In the past, there was conjecture that extraterrestrial life might be on other planets. The idea that the Earth is not the center of the universe was advanced by Copernicus, Kepler, and Galileo. It was inevitable that thoughts of other solar systems would surface once it was realized that our planet is only one of many orbiting a solar nucleus. Giordano Bruno was arguing by 1584 that there had to be countless suns and planets circling each other. The next logical step was to suggest that life might exist on some of those innumerable planets, a novice concept. The possibility of extraterrestrial civilizations on Venus and Mars, Earth's closest siblings, started to be seriously considered by the educated world by the 19th century. Ideas ranging from a warlike race of Martians determined to conquer Earth to the possibility of a tranquil paradise growing beneath the clouds of Venus were sparked by the human tendency toward wonder and fear. American astronomer Percival Lowell claimed to have spotted lengthy canals that may have been constructed to carry water from the poles to arid equatorial regions, which stoked conjecture about intelligent life on Mars. This encouraged early 20th century science fiction authors like Edgar Rice Burroughs to envision a technologically sophisticated but dying, warring world. In general, the speculations regarding life on Venus were more benign. The planet was obscured by thick clouds which fueled romantic visions of a lush biosphere. From Robert Heinlein's vision of a carboniferous swamp to Ray Bradbury's short stories about constant rain, the Venus of science fiction was typically viewed as a warm, dripping wet water world that might sustain a profusion of alien plants and animals. The onset of the space age brought reality into focus. Cameras taking pictures of Mars and Venus showed no evidence of either, and robotic probes sent to our nearest celestial neighbors shattered ideas of sophisticated civilizations or even widespread, if unintelligent, life forms. When humans landed on the Moon for the first time in 1969, they found it to be as barren as telescopic observation had shown. The possibility of life on Mercury also appears remote because the planet has a topology similar to the Moon and undergoes drastic thermal changes. As scientific information about the gas giants and their moons grew, it became clear that no other planet in our solar system has Earth-like conditions. This means that our planet, at least within 4 light-years of our nearest star, is unique and rare. This discovery, which is undoubtedly depressing for individuals who hope to discover sister systems of extraterrestrial life, was counterbalanced by the realization of the universe's immense size. There must be solar systems everywhere in a universe that is more than 13 billion light-years across, even though our solar system, aside from Earth, may not be particularly conducive to life. The idea that solar systems are ubiquitous in the universe seems plausible given the mounting evidence over the last 10 years that planets in our galaxy orbit other suns. Given enough solar systems, planets as conducive to life as Earth must exist elsewhere, even if Earth-like planets are uncommon. We are more likely to discover and identify life in other worlds resembling Earth because we know it exists there. This is the reasoning behind the terracentric search for life on other systems' planets and the hunt for planets that resemble Earth. It provides the motivation to follow the water. It is the foundation for searching for planets with liquid water and protective atmospheres, ideally on medium-sized rocky planets with stable, nearly circular orbits and mild seasonal and diurnal cycles. It backs up the idea of the stellar habitable zone, which holds that life can only exist on planets just far enough from their central star to have Earth-like conditions. The hunt for life in our image is a perfect fit for it. The alternative reasoning is based on the idea that life on Earth might not be a sign of life elsewhere, which means that the circumstances that support and sustain life here shouldn't be viewed as limitations. According to a more complex view, human life is not typical of the majority of life on Earth. Rather, the vast microbial ecosystems that exist beneath our feet, in our oceans, and deep within the Earth's crust are the standard for life on most planets, including our own, with larger organisms that catch our attention being merely exceptions. In their groundbreaking book, Rare Earth: Why Complex Life is Uncommon in the Universe, Peter Ward and Donald Brownlee, an astronomer and paleontologist at the University of Washington, attempted to combine various models into a coherent theory. They argued that complex life will probably only arise under particular Earth-like conditions resulting from unique circumstances, and they characterized the rare Earth hypothesis as the paradox that life may be nearly everywhere but complex life almost nowhere. Complex life must be rare since such a combination is statistically unlikely. On the other hand, microscopic or non-complex life demonstrates exceptional environmental adaptability. The universe may be home to microscopic forms of simple life because extreme environments, by terracentric standards, are common. In the following chapters, we will discuss these two main schools of thought and outline our approach to systematically studying cosmic biology. However, it is crucial to understand the historical background that informs our current understanding, especially about the formation of different possible extraterrestrial life habitats, such as gas giants, rare Earths, and snowball planets. We will briefly introduce the universe's history and the evolution of our solar system. We propose that life cannot exist close to an active star because the chemical reactions necessary for life at such high temperatures are unstable. As such, cosmic biology is planetary, including satellites, planets, and planetoids. So, we start by looking at how planets came to be. The idea that the universe has a finite origin has not historically been widely accepted by science. Fred Hoyle, the renowned cosmologist, advocated for the continuous and eternal production of energy and mass throughout space. However, there is growing agreement among scientists that the universe originated from a single point in space and time. The universe's current expansion, the fact that the oldest objects are located at its edges, and the persistence of electromagnetic radiation from the universe's turbulent beginning, often referred to as the Big Bang, as Hoyle ironically called it, are examples of supporting evidence. The current scientific theory of the universe's creation is so outrageous and unbelievable that it surpasses any myth or metaphor in world religions. The Big Bang theory, which holds that all matter and energy in the universe originated as follows, is grudgingly accepted by most scientists until evidence to the contrary is found. Before the universe was created, there was no such thing as space or time. Our universe began with such violence and speed some 13.7 billion years ago that it was impossible to tell matter from energy. The universe grew from a single point to a spatial volume of 100 billion kilometers at a temperature of 10 trillion degrees Celsius in the first microsecond of its existence. Due to this explosive spatial expansion, subatomic quarks and other matter could separate from pure energy and combine to form baryons, protons and neutrons. In the first second of the universe, neutrons began to change into protons by releasing more electrons. They started to combine into pairs of 2 protons and 2 neutrons, creating the nuclei of potential helium atoms as the proton-to-neutron ratio got close to 7:1. Within a few minutes, this process absorbed almost all free neutrons, leaving a significant excess of free protons, which make up hydrogen atom nuclei. For protons and neutron-proton aggregates to absorb free electrons and create the first hydrogen and helium atoms, the universe had to cool for over 200,000 years to reach 2,700 degrees Celsius. The opacity weakened as the thick cloud of electrons merged into new atoms, and photons could move across the now 100 million light-year expanse of space. By 300 million years into its existence, the universe was almost, but not completely, uniformly populated with a large amount of energy, a lot of dark matter, whose properties are still unknown, and a small amount of helium, lithium, and hydrogen, the 3 lightest elements. The anomalies in the density of the normal matter in the universe were subject to the action of gravity, another fundamental force of nature. Helium and hydrogen clouds began to collapse in regions with higher gas concentrations. Gravity pulled the atoms into a sphere once these clouds reached a certain mass, which eventually compressed enough to start the fusion of hydrogen and helium, releasing energy from light and other particles and electromagnetic radiation. The first stars appeared as a result. The stars of the early universe were much larger than modern stars. Due to the increased gravitational forces, their cores experienced accelerated fusion processes. After the hydrogen at the core ran out, helium atoms started combining to form heavier elements like carbon, nitrogen, and oxygen. Atomic nuclei broke apart under the tremendous gravitational pull of the biggest stars. The higher density of heavier elements in the cores caused this phenomenon. The star eventually broke apart due to the atoms' subsequent explosive pressure on one another. Consequently, the heavier elements that these early stars produced were thrown into space. This produced lighter elements and metallic dust particles that floated around and combined with helium and hydrogen gas. The cycle would eventually be repeated when these clouds of gas and dust collapsed to create the next generation of stars, which would be more chemically enriched. The heavier elements that would eventually make up all of the universe's living things and celestial bodies were produced by this process. According to the laws of angular momentum, rotational motion is initiated when matter self-collapses. In many cases, centrifugal force retains some matter, as dust and gas fall into a protostellar mass's gravitational well, preventing it from accreting to the central star. The matter at the periphery rotating and flattening into a disk results in a spherical core encircled by a distribution of material orbiting in a planar configuration. Dust particles, water molecules, and other compounds formed in the void collided more often as the interstellar space flattened. These particles often stuck to each other because of the intense cold at the center of their orbital trajectories, far from their burgeoning suns. Once more, discontinuities affected the process, with slightly denser grains gaining mass more quickly than their surroundings. Over millions of years, this pattern continued, causing aggregates the size of boulders to combine into larger boulders to form planetesimals, which eventually grew to a diameter of several kilometers. Planetesimals have enough mass to attract other objects with gravity. The attraction of the smaller planetesimals to the larger ones initiates a runaway accretion process. As a result, this process increases the chances of a few planetesimals becoming protoplanets in a comparatively short period. The growing number of protoplanets attracts more fragments from the early protostellar disk. The densest elements, like iron and nickel, could descend to the core of the sufficiently large newborn planets due to the intense bombardment of matter and energy that melted their interiors. A solid surface formed from an outer crust, made of lighter metallic compounds, such as silicates, was subjected to intense bombardment for millions of years. The planet's surface received matter and energy from this process, and the heavier elements' radioactive decay produced heat inside. When the planetesimals gathered to form the protoplanets, they rotated like the protostellar disk, sometimes generating satellites around their central planets as the planets orbited their central star. Planets accumulated gases like nitrogen and hydrogen as they formed. Whether these light gases would disperse into space, stay as atmospheric gases, or be subjected to enough gravitational pressure to form a liquid shell encasing the planet's rocky core depended on the planet's size, temperature, and proximity to the central sun. The latter group developed into clearly large gas giants. Approximately 4.6 billion years ago, our solar system began to form. A slightly larger than average sun, 4 terrestrial planets, Mercury, Venus, Earth, and Mars, 4 gas giants, Jupiter, Saturn, Uranus, and Neptune, and a variety of smaller celestial bodies, including a binary dwarf planet system, Pluto and Charon, were all created by the protostellar disk that formed our local region of the universe. Except for the two innermost planets, every planet in our solar system has a satellite. Most satellites are found on Jupiter and Saturn, the two largest planets. In contrast, the smaller inner planets have one moon, Earth, two moons, Mars, or none at all, Mercury and Venus. This might be because their parent planets were less material-rich, or satellites are difficult to maintain in stable orbits so near the Sun's powerful gravitational pull. In addition to discovering numerous new solar systems, scientists can observe protostellar clouds at various stages of formation from a distance. This demonstrates how the universe is continually and repeatedly created. It wasn't until 1992 that we discovered the first exoplanets. Before that, we had no reason to doubt that the logic of our own system, smaller terrestrial planets with weaker atmospheres close to the Sun, while gas giants with larger atmospheres farther away, was a universal law dictating the structure of solar systems worldwide. The discovery of gas giants larger than Jupiter orbiting their central stars at distances much closer than Earth's orbit around the Sun disproved the assumption. We are now finding planets about the same size as our terrestrial counterparts, which are much harder to find. However, there is ample evidence that other solar systems have different planet configurations, different from our own supposedly logical arrangement or the fast-rotating gas giants that were first found near their central stars. This includes many exoplanets orbiting various stars, such as red dwarfs, giants, and multiple star systems with extremely eccentric orbits. While writing this book, we discovered about 500 exoplanets outside of our solar system, and we anticipate that number to double in the coming year. Recent advancements in exoplanet research are exemplified by the discovery of the Gliese 581 planetary system. At least 4 planets, ranging in size from 1.9 to 13 Earth masses, orbit the M-type star or red dwarf Gliese 581, which is 20.3 light-years away from Earth. These exoplanets range in size from Earth to Neptune, and are most likely rocky bodies with thick atmospheres. Many exoplanets have exomoons, and some satellites must be the right size and makeup to support life. Without thoroughly studying a wider range of solar systems, we cannot determine the frequency of rocky planets, water worlds, barren moons, icy satellites, and gas giants. We have good reason to believe that they are all out there somewhere. Luckily, our solar system has examples of each, so cosmic biology began by focusing on the planetary environments closest to our own. In its most extreme form, the rare Earth model holds that only the conditions on Earth are suitable for life. Those conditions are the result of a combination of unlikely coincidental factors. Because of this, planets that resemble Earth are rare, and so is life. Instead of focusing on the likelihood of any life existing, Ward and Brownlee's book highlights the possibility of complex life emerging. On this basis, ideas like the galactic habitable zone and the stellar habitable zone are based. These ideas suggest that rocky planets with Earth-like features are necessary for life. The Earth is indeed unique in our solar system. The Earth's ideal orbital distance from the Sun allows for adequate absorption of sunlight while avoiding atmospheric overheating. It is big enough to keep the atmosphere dense enough to protect against all but the biggest meteorites, but not so dense as to permanently trap heat. The very high atmospheric oxygen concentration promotes efficient energy metabolism, and the ozone produced from that oxygen reduces damaging UV radiation. Most of the time, liquid water is present on Earth's surface due to the planet's average temperature of around 15 degrees Celsius. The tilt of Earth's axis relative to the plane of its solar orbit causes seasonal variations in temperature, precipitation, and oceanic and atmospheric currents. Axial rotation and the gravitational pull of the Sun and Moon cause cycles to occur more frequently, resulting in daily variations in temperature, tides, and light and dark. The biosphere becomes cyclical as a result of these changes. The complex land topography and the worldwide land and water meeting points produce various environments. These are the complexities that allow life to break up into ever-increasing complexity. The flaw in the rare Earth model is the assumption that planets with various environments are uncommon, rather than the widely held belief that diverse environments are necessary to evolve biological complexity. They might be. A definitive response is currently impossible due to insufficient data. Despite this, we conclude that the emergence of complex life is rare. However, this does not mean that the emergence of life in any form is rare. Thus, it is not very beneficial to restrict the habitable zone to a solar system where rocky planets can sustain liquid water. The idea of the galactic habitable zone, where rocky planets can exist, becomes easier to understand if one assumes that solid substrates in contact with liquids are necessary for the emergence of life. However, we cannot exclude many possible worlds outside the galactic habitable zone, as the environmental requirements for life remain poorly defined. Because life that develops under similar conditions is more likely to be identifiable, it makes sense to use the stellar habitable zone as a starting point for searching for extraterrestrial life. Although the idea of a galactic habitable zone is intriguing, it is meaningless in light of our current technological capacity to look for extraterrestrial life. Compared to microorganisms, multicellular macroorganisms on Earth require a smaller range of environmental conditions to survive. The evidence for life on Earth suggests that multicellularity and large size evolved over long periods in relatively stable conditions on a planet with liquid water and continents. It's still unclear if that time and those particular circumstances are required to develop biological complexity. Furthermore, we cannot assess how uncommon Earth's unique geophysical conditions are in the cosmos. However, the belief that big, complex creatures are uncommon, compared to the much higher number of microorganisms on other planets, is likely correct. According to the life unseen model, the universe's most common types of life are invisible. They are too small for humans to see without assistance. Their existence is verified by advanced methods like metabolic analysis, biochemistry, and microscopy. Compared to the life forms that usually draw our attention, the hidden world of life on Earth is far more vast, widespread, varied, and robust. The simplest and oldest unicellular organisms, prokaryotes, may have a biomass equivalent to all plants on the soil and ocean floor. When larger plants, animals, and fungi are considered, as well as more complex microscopic organisms like protists and yeasts, the overall biomass is significantly greater than that of all visible plants and animals. The smallest organisms exhibit the greatest ability to adapt to harsh environmental conditions. Some prokaryotes can endure at temperatures close to the boiling point and below the freezing point of water. Across the pH range, they flourish in acidic pools and alkaline lakes. These prokaryotic organisms can withstand radiation levels well above human tolerance, prolonged desiccation, extreme pressures, and the vacuum of space. These extremophiles provide very little proof of a significant habitable zone. Physicochemical conditions obstructing normal chemical interactions have neither created life nor predicted its production. Apart from that restriction, living processes are not inherently constrained. The existence of extremophiles on Earth has lessened the importance of the stellar habitable zone in space. Since extreme conditions on Earth are common on other planets, extremophiles in those environments should be considered a likely and common occurrence. As such, a habitable zone might not be crucial in life unseen. According to observations, extremophiles on Earth are typically small, though not always microscopic, indicating that they could be tiny in any setting they live in. This suggests that they will continue to be invisible, at least directly. Finding biosignatures of undiscovered life is a major area of interest in astrobiology. and technology is constantly advancing in this area. For this reason, there is good reason to expect to find isolated life forms, if any, as the search for alien worlds intensifies. Our planet demonstrates that the unseen life model for a biosphere primarily comprises sequestered microscopic organisms, and the rare Earth model of complex life coexists. However, there is no symmetry in the relationship. Simpler microscopic organisms almost have to coexist with complex life. However, worlds with biospheres made entirely of microscopic ecosystems and completely lacking larger, more complex organisms are unquestionably more common. Assuming that these two models outline the bounds of possibility, historical and contextual factors will determine the type and diversity of life on any given planet. The origin of life and the conditions that allowed it to evolve are determined by history. The type of life that is currently viable depends on the circumstances. Mars, Venus, and Earth provide a powerful example. Although they are different, Earth and Venus are planetary siblings. The rocky planets are almost the same size and orbit the Sun in adjacent orbits. They were formed from protostellar matter. According to our knowledge of how the solar system formed, both were heated by the Sun and first struck by meteorites and asteroids that carried water and organic materials. At the moment, Venus's surface is a harsh place with intense heat, while Earth is rich and has a diverse biosphere. How could two worlds with similar origins differ greatly in their ability to support life? History clarifies some distinctions. One event in the distant past caused Venus to rotate opposite the Sun and Earth. Any water and atmosphere present at the time might have been completely destroyed by Venus. Intense volcanic activity reformed the planet about 1 billion years ago, producing a dense sulfuric acid and carbon dioxide-rich atmosphere. This atmosphere eventually developed into an uncontrollable greenhouse environment. The current climate makes matters worse because Venus's closeness to the Sun and the Sun's increasing energy output intensify the greenhouse effect. Venus's closeness to the Sun slows down its rotation, which eventually causes the planet to become tidally locked, ensuring that the Sun always sees the same hemisphere. At the same time, life is flourishing on Earth as it orbits the Sun at the ideal distance, with an atmosphere that provides protection and keeps liquid water on the surface, but not too many greenhouse gases to permanently retain heat. Compared to Venus and Earth, Mars orbits 50% further from the Sun. Because Mars is much colder and has a much thinner atmosphere than Earth, its surface appears to be as lifeless as Venus's. However, it began its temporal journey as a warmer, watery planet. Due to its smaller size and greater separation from the Sun, the planet apparently could not maintain its previous, denser atmosphere, which led to the exhaustion of its vast surface oceans. As a result, we see the difference between 3 planets that formed simultaneously in the same region of the solar system, and have 3 different outcomes in terms of their ability to support life due to historical and contextual influences. There may still be life on Mars or Venus, but it will be very different from life on Earth. This book explains why this is possible and investigates how different life histories could appear in different parts of our solar system and the cosmos. We illustrate cosmic biology by looking at a planet's history from its beginnings and the development of its geophysical properties up to the present. This will give us a framework for the possible evolution of life and help us tell the story of the planet's history and conditions. Using fundamental ideas from ecological and evolutionary theory, we will then hypothesize about several existing ecosystems in those worlds today. To guarantee a common understanding, we must first formally define life. Next, we must look at the basic physics and chemistry concepts that form the basis of the science of biology. Since ancient times, there has been speculation about the possibility of extraterrestrial life on other planets. Our growing understanding that Earth is not alone among the planets of our solar system, that solar systems like and different from ours are common in our galaxy, and that the total number of galaxies is almost uncountable has given credence to the idea that we are not alone in the universe. The space and time we occupy were created by the finite beginning of our universe. These books do not cover the main model of the universe's origin, which includes many viewpoints. Nevertheless, scientists agree on the fundamental processes by which planets and stars form. This clarifies the structure of our solar system, which consists of a binary dwarf planetary system in the center, 4 terrestrial planets in the center, and 4 gas giants on the periphery. However, recent findings challenge the notion that our solar system structure is normal. The presence of liquid water on Earth's surface sets it apart from all other known planets. This results from its mass, distance from the Sun, and relationships with other planets in the solar system. Because of its long-term stability, life has evolved and diversified into a wide range of complex macroorganisms and a sizable biomass of microorganisms. This paradox that life may be almost ubiquitous but complex life is exceedingly rare is what Peter Ward and Donald Brownlee dubbed the rare Earth hypothesis. It explains the circumstances that led to the evolution of complex multicellular life. The Earth's biosphere demonstrates that the range of environments that microorganisms can live in is less than the stringent requirements for complex microorganisms. It is still unknown, though, if Earth-like environments are the only ones that can foster the development of complex life forms. Whether Earth-like conditions are especially rare is still unclear. If one recognizes that many environments could harbor microbial life, the rare Earth model is a useful starting point for investigating the possibility of life in different parts of the universe. Mars, Venus, and Earth are examples of how historical circumstances and context impact the probability of life forming, developing, and diversifying on a given planet. These 3 planets, which began as rocky planets orbiting the same central star simultaneously, have significantly different capacities to support life today. This book will use ecological and evolutionary theory to explain how and what life might look like on these other planets and satellites in our solar system and possibly unexplored worlds. Our solar system's planets were formed from clusters of stardust circling a central sun, and they began their evolutionary journey with a varied mixture of energy and chemistry. Life on Earth began in this cauldron and evolved into various creatures that live on the surface, fill the atmosphere, and seep into the soil and oceans. Henceforth referred to as evolution, organic evolution refers to the historical process that led to diversification. This book explores the possibility that that process occurred in worlds other than our solar system. Despite our innate understanding of life, it is difficult to define it in a way that distinguishes living things from other objects in the natural and artificial worlds that share many traits. Because of the enormous diversity of life on Earth, it is impossible to characterize every living thing in terms of size, shape, or appearance. Thus, we encounter characteristics like growth, ingestion, respiration, excretion, autonomous movement, and reproduction. The problem is that for every quality we can think of, there is an example that is clearly not alive. Both volcanoes and crystals grow. Cars use gasoline and release carbon dioxide and water. Until their durations exhaust, hurricanes and forest fires transform energy into independent, self-sustaining processes. Our publisher has created several identical copies of this book because clones can reproduce. But nobody would argue that life exists in clouds, crystals, cars, or office copiers. One could be tempted to describe life in the same way that Supreme Court Justice Potter Stewart described his perception of pornography in 1964. I know it when I see it. The problem lies in our failure to recognize life, even on our planet. Is it possible to tell whether a tree without leaves is dead or alive in the winter? We may not be familiar with life and its functions on planets with different ecosystems and geological histories than on Earth. A formal definition that captures the essential features of living things and distinguishes them from similar but non-biologically living entities is what we need. Existence prioritizes procedure over content. The complex parts of living things are unique to the biological world, but come from the same atoms and molecules that make up the inanimate cosmos. After death, an organism's composition is slightly different from its living states, but it no longer possesses the quality of life. In the same way, wind is more than just air, and life is more than biochemistry. The main characteristic of life's complexity, the most fundamental bacterium, is an intricate metabolic processor, information repository, storage facility, and active agent. Think about the greater complexity of an organism, like the human body or a redwood tree. In fact, many inanimate objects, including cars, computers, and skyscrapers, are complex. However, the complexity of living things is greater than those examples in two respects. A living cell is more complex per unit volume than a computer circuit board. Second, the company can support itself. A living cell maintains its unique and complex complexity, but when a car breaks down or a building window breaks, human intervention is needed to fix it. The ability of life to take intrinsic action is the foundation of our understanding of it. The wind propels a dead leaf, which can still not move independently. Even though it was an essential part of the tree, it developed, oriented itself toward the sun, took in water and carbon dioxide through its pores, changed its color in the fall, gathered nutrients from other parts of the tree, and created food to keep the whole thing healthy and growing. At least in primitive ways, even the simplest cells respond to their environment by gravitating toward positive stimuli and away from negative ones. However, our intuitive understanding of the significance of intrinsic action may be misleading unless we clarify. When given the go-ahead, a car can operate itself. A computer screen can display a lengthy, complex audio and video sequence when properly programmed. Nobody would claim that the computer or the car has life. As a result, our definition of life needs to distinguish between a computer, a car, and a tree. Ultimately, life can replicate itself. The word self element is crucial. Living things can use the raw nutrients they absorb from their environment to create an almost exact duplicate of themselves. Once more, we must distinguish between similar natural phenomena and those occurring in the artificial world. When submerged in an appropriate mineral solution, the crystals replicate their crystalline structure and multiply. When cells divide through mitosis, a cloud may split into two. The information on this page can be accurately reproduced by a photocopier. The spread of computer viruses, whose names imply a close resemblance to real biological processes, is a disturbing analogy to biological replication. All of these examples, however, can be distinguished from the self-replicating properties of living things. Both the cloud and the crystal have no boundaries and can grow indefinitely. When an outside operator inserts documents into the machine and presses the appropriate buttons, documents can be accurately replicated. However, they cannot replicate themselves. Since the computer virus is only a programming code with no physical form, it only spreads information about virtual reality when an outside operator turns on the computer and types commands into the keyboard. Examining the dynamic processes of life requires us to recognize that reality comprises distinct entities that exist separately in space and time. In actuality, a living organism is an entity with dynamic properties. A living organism's physical remains, such as fossils, offer unquestionable evidence of its past existence even after it has passed away. On the other hand, a spore or seed may be very inactive before germination, but it can become a distinct living being. A fossil or spore offers concrete proof of past or possible life, even though it is not technically living. Therefore, existence involves a dual essence. A living thing is a process as well as an entity. Since life is a noun that needs to be explained by other nouns, defining it is a semantic challenge. However, being alive can only be described by certain verbs. This book examines the evolution of distinct kinds of organisms in alien environments while imagining real beings. These beings must, however, have the unique characteristics that characterize the living state. The cell is the basic life unit with all living things' traits. The bulk of biomass on Earth is composed of unicellular life forms, and as we will show, microscopic life forms may be more prevalent on many other planets. According to this book, organism includes unicellular and multicellular life forms. All living things on Earth and those thought to exist on other worlds share three traits that distinguish them as such. At first, they are discrete beings, separated from the outside world by physical barriers that separate their well-structured interiors. The boundary keeps the complex interior of the organism from equilibrating or dispersing haphazardly in its chaotic surroundings. The fact that living things are more complex than their surroundings sets them apart. The boundary distinguishes the living thing from a cloud, crystal, or ocean wave by preserving its constant form and shape. As we search for extraterrestrial life, we will imagine physical beings with unique shapes and boundaries that set them apart from their surroundings. The boundary of a living thing acts as a physical barrier and a gatekeeper for substances entering and leaving its interior. The external environment and the internal environment have different concentrations and compositions. Pores of different sizes and transporter molecules that preferentially target particular substances, such as sugars and essential amino acids, make this possible. This further distinguishes between the living and non-living parts of the organism. Furthermore, certain environmental molecules important to the organism, such as food, toxins, and the scents of mates and predators, are recognized by receptors at the boundary surface. This gives the surface a biological uniqueness that affects that particular species' usual behaviors and responses. Second, living things draw energy from their environment to maintain a high level of internal organization and carry out necessary functions. It takes work to keep an organization going. A living system needs a constant flow of energy, or work, to stay in a highly ordered state. This means repairing damaged structures, replacing broken molecules, and maintaining the equilibrium of ionic concentrations on opposite sides of a membrane. Similarly, energy is required for all actions, such as growth, movement, and signal emission. A living thing is, by definition, an emitter and an energy consumer. Indeed, wildfires, hurricanes, and cars transform energy and impact the environment. The reactions inside a living cell are complex and involve many intermediate steps and chemical compounds, in contrast to the relatively simple and explosive reactions that occur in an automobile engine or the uncontrolled release of significant potential energy that occurs during hurricanes or wildfires. This makes it easier for energy to be released gradually and under control. Together, we refer to the complex interplay of these chemical processes as metabolism. The metabolic conversion of energy is clearly localized, compartmentalized, and reduced compared to the previously mentioned non-living examples. The metabolic processes of a bacterium are too small to be seen without a microscope, but they are far more complex and varied than the energetic but chemically simple light and heat from fire, the large-scale explosions in an automobile, or the simple but widespread turbulence of a hurricane. Furthermore, living things have self-regulating metabolisms. When an organism produces more energy than it needs right away, feedback mechanisms stop it from producing more. If the ionic concentration inside an intracellular compartment becomes unbalanced, it may transport additional ions in or out until it restores equilibrium. The living system can provide all of these feedback and regulatory systems. Like the hurricane and the forest fire lack self-control, The vehicle requires an outside agent, the driver, to control its speed and direction. Third, replication in living things is almost exact and completely self-sufficient. This definition's main flaw is that living children are not merely imitations of their parents, nor do they share many of the same characteristics. When biological reproduction occurs, the resulting organisms are typically nearly the same size at maturity and form as their parent organisms. Here, they stand in contrast to the formation of mineral crystals, which continuously gain mass, or to tornadoes, which create new formations that might not be as large or powerful. The second important fact is that a living can use only its available energy to duplicate itself based on the raw materials or nutrients it consumes. This process is controlled by an internal information store found in the DNA of every living cell, which replicates and passes it on to every generation after it. Though it is unclear if DNA or a similar material performs a similar role in extraterrestrial life, it is clear that certain information storage and retrieval systems are necessary for the exact replication that is a feature of biological reproduction. The fact that non-living replicas made by humans and machines are ubiquitous makes it clear that reproduction must be autonomous to be considered a living process. A new home is built from the same blueprint as an old one. Cars are made on assembly lines, and photocopying allows for the endless replication of text and images on paper. These scenarios entail assembling pre-existing items or transmitting data via directives for a specific series of steps that will yield identical outcomes to the originals. However, each case requires outside agents and information for construction or replication. If a robot can replicate itself and give the replica the ability to replicate further, it might be considered alive. But until then, it only satisfies the remaining requirements for being a living thing. Life is considered exuberant in contrast to the relative simplicity of sand, stones, and air. In their moving attempt to describe the essence of life, Lynn Margulis and Dorian Sagan described it as planetary exuberance, a whirling nexus of growing, fusing, and dying matter gone wild. It certainly consists of a substance that is self-activating. Despite its remarkable powers, a living thing on Earth comprises limited components. More than 96% of its biomass comprises carbon, oxygen, nitrogen, and hydrogen. A creative chemist would have almost all the elements needed to create a living organism, except a few trace elements, if calcium, phosphorus, sodium, potassium, chlorine, and silicon were included. However, nobody has managed to do this. You can buy the ingredients at any pharmacy. They can be given separately and dispensed. The resulting slime can be watched as it moves. It won't. The combination of oxygen, hydrogen, nitrogen, and carbon will continue to exist with the same inert materials. People have therefore believed that there must be an immaterial component that gives the chemicals life since they first learned about the physical world. Matter and energy alone cannot adequately explain what it means to be alive. Scientists gradually questioned this idea in the 19th century by clarifying the various roles of living things as a unique chemistry instance. It was common for ions and atoms to interact in aqueous solutions in inanimate test tubes, but they agreed that these organisms displayed complex and intricate behaviors. The notion that life is a particular instance of a small number of known, or at least intelligible, chemical systems gradually replaced the notion that life is composed of matter imbued with an intangible vital force. Therefore, what makes the chemistry of life unique? First, note that our definition of living things does not mention chemistry. The purpose of this deletion was to avoid any prejudice that our knowledge of earthly life might introduce into our assessment of other planets' living systems. The glaring homogeneity of life on our home planet would make this bias noteworthy. The compositional level of life can be summed up as carbon-based polymeric and ionic chemistry in solution. which applies to all living things, including humans, baboons, and bacteria. The 4 main elements in Earth's living systems are among the 8 smallest atoms: oxygen, nitrogen, carbon, and hydrogen. Together with calcium and magnesium, a second group of larger atoms makes up most of the mass of known living things. Except for helium, the 4 main components of life also constitute 4 of the 5 most common elements in the universe. Atoms comprise a central nucleus densely packed with positively charged protons and neutrons. These are accompanied by negatively charged electrons spaced apart from the nucleus and as numerous as the protons. Electrons organize themselves into orbitals, which are distinct areas or energy levels. Up to 2 electrons can be symmetrically arranged around the nucleus in the first electron orbital. Hydrogen, the most basic atom, has just 1 electron. Atoms with at least 3 electrons require a secondary orbital level with a more complex structure. It has 4 suborbitals, each of which can hold 2 electrons. However, electrons are positioned to be as far apart as possible. Therefore, when the second tier's total number of electrons is less than 8, the unpaired electrons scatter into different suborbitals. The first 2 of carbon's 6 electrons are located in the first energy level, and the other 4 are positioned in the second energy level's 4 suborbitals to maximize their distance from one another. The unique chemistry of carbon is caused by its 4 valence electrons. 2 or more atoms are joined by a chemical bond to form molecules. Biomolecules are compounds found in living things that are often, but not always, features of living systems. Because of their high levels of organization and complexity, living systems require large, complex molecules as constituents. One of the most important characteristics of biomolecules, their polarity, must be discussed before looking at the different classes of biomolecules. Because of their similar electronegativities, hydrogen and carbon share electrons almost equally when they form a bond. Because of the uniform distribution of its electrons, this molecule keeps no area from becoming more or less negatively charged than others. This molecule is, therefore, nonpolar. A prime example of a nonpolar molecule, methane, has a central carbon nucleus surrounded by 4 symmetrically arranged hydrogen nuclei. Since these nuclei share electrons equally, no part of the molecule has a higher negative or positive charge than any other part. On the other hand, water is a polar molecule, since all of the electrons from the 2 less electronegative hydrogen atoms are drawn to the highly electronegative oxygen atom. The adjacent suborbital is already occupied by the oxygen nucleus. This state indicates that the negatively charged electron cloud adjacent to oxygen cannot be balanced by the positively charged protons from hydrogen. Water is an asymmetrical molecule with a noticeable negative region at the back and 2 positive regions at the front. Carbon can form polar molecules when bonded to highly electronegative elements like oxygen or nitrogen because they draw carbon's electrons. Methanol has a negative charge about the attached hydrogen at the molecule's terminal end because the oxygen atom takes electrons away from hydrogen and carbon. However, because the electrons are evenly distributed between the hydrogen and carbon, the molecule's CH0 end is not polar. Carbon is Earth's 4th most common element and the universe's 3rd most common element. In addition to its accessibility, the following characteristics make it an important component of living systems. 1. Up to 4 other atoms can simultaneously form chemical bonds with carbon, creating various molecular configurations. The simplest organic molecule, methane, which is made up of 1 carbon atom bound to 4 hydrogen atoms, is an example of how carbon's partners can be the same. On the other hand, carbon can form bonds with 4 different atom combinations to create a more complex structure, like the amino acid alanine. 2. Covalent bonds are created when carbon shares its electrons with other atoms fairly equally. Carbon can easily form bonds with atoms that have a higher or lower electronegativity than it due to its moderate electronegativity. Its ability to partially release its electrons or attract the electrons of another atom suggests that it can interact with other compounds rather easily. However, those bonds are still stable, because carbon does not give up its electrons or usurp them from another atom. Carbon is the main component of a wide variety of organic molecules that are both stable enough to endure long periods and flexible enough to change when necessary. 3. Another benefit of carbon is its low electronegativity, which makes it relatively easy to give and receive electrons, a process known in chemistry as oxidation and reduction. Because of this characteristic, carbon can effectively transfer tiny energy packets. In the following section, we will delve deeper into this subject. 4. Water is the most readily available liquid on Earth and possibly the entire universe, and carbon-based compounds are good at interacting with it. Because of oxygen's affinity for electrons, which makes the oxygen end of the molecule more negatively charged than the hydrogen end, which keeps its positively charged protons, water is a polar molecule. Ethanol dissolves in water when a polar molecule like ethanol is added to a polar solvent like water because the two molecules' comparatively positive and negative parts are drawn to one another. Our classification of polar molecules like ethanol as hydrophilic or water-loving follows this. High solubility makes it easier for biomolecules like carbohydrates, amino acids, and nucleic acids to disperse in water. Because they lack a definite negative or positive region, carbon compounds bonded to hydrogen or to themselves are nonpolar. When water comes into contact with a nonpolar molecule, such as the lengthy hydrocarbon chains found in vegetable oil, the nonpolar carbon chains push the polar water molecules away while remaining adjacent. The oil is called hydrophobic because it tends to form insoluble droplets in water. This characteristic is advantageous for components of living systems that create barriers in aqueous solutions. In conclusion, hydrophilic carbon compounds participate in the intricate processes of life and dissolve readily in water. Conversely, hydrophobic carbon compounds form solid barriers that stop water and other molecules from passing through. These barriers establish the enclosures and boundaries required to distinguish living systems. We need to assess whether silicon, the larger sibling of carbon in the same group of periodic tables, has the capacity and flexibility to support alternative biochemistry. The abundance of silicon in living things like plants and marine diatoms gives the idea of silicon-based life some plausibility. Silicon-based biology is a common theme in science fiction. With 4 electrons in its orbital spaces, silicon is comparable to carbon and shares many chemical characteristics. Under circumstances very different from Earth's, silicon might be a useful backbone and intermediate biomolecule element. Such circumstances might exist, so we will briefly review the potential outcomes. Atoms of silicon and hydrogen combine to form silanes. Silan, SiH4, the analog of methane, CH4, is the most basic compound in the carbon-based realm. It is theoretically possible for silanes to form long CC side chains that resemble carbon polymers. Silicon-based polymers are less stable because the bonds between silicon atoms are weaker than those between carbon and silicon. Silanes decompose into SiHP gas molecules at extremely low temperatures. This suggests that a very low temperature, much lower than the freezing point of water, is required for polymeric silanes to remain stable. The units that make up silicates are Si-O4-4, the fundamental component of rocks and many minerals, silicon tetrahydroxide, Si open parenthesis, OH close parenthesis, subscript 4, is the most stable example at Earth-like temperatures. It usually takes the shape of a long polymeric crystal that forms strong minerals at temperatures as high as those found in a molten volcano. Since the SiO bond is much stronger than the CO bond, any interactive chemistry must occur at very high temperatures. Silicon would absorb oxygen more quickly than carbon in an oxygen-saturated environment, rapidly converting it to its inert mineral state. Silicones are molecular mixtures of hydrogen, carbon, oxygen, and silicon. These molecules are stable at temperatures lower than those required for most compounds to remain liquid, as predicted by the repeated OSiO units that make up the silicone backbone. The process of creating organosilicon compounds in a laboratory is time-consuming and intricate. They are far less common in nature, where they primarily form stable structures rather than interacting with other molecules. If silicon were a better basis for life than carbon, the world would be extremely cold, oxygen-free, and have a stable liquid apart from water, for silanes, or be so hot that the only liquid would probably be molten minerals, for silicates. Extreme temperatures reduce the possibility of intricate chemical reactions similar to carbon-based metabolism in both cases. The feasibility of life forms based on silicon is contradicted by empirical evidence. We have yet to find any life forms solely based on silicon, even though silicon is much more common than carbon on most rocky planets, including Earth. Many complex organic compounds, including amino acids, the building blocks of proteins, have been found in meteorites recovered from space, but no complex silicon polymers have been identified. On the other hand, silicon is a trace element that gives many organisms their structural rigidity. Examples include animal bones, plant stems, and the skeletons of echinoderms and diatoms, including sand dollars. As explained later, these examples point to a more important role silicon played at the beginning of life. Biomolecules assembled into sizable aggregates are known as macromolecules. Their distinct composition determines how they function in biological processes. For proteins, this process produces a distinct three-dimensional structure. For nucleic acids, it produces a particular linear sequence of variable subunits. The monomers of the polymer protein are amino acids, whereas the monomers of the nucleic acid polymers, DNA and RNA, are nucleotides. A macromolecule can be assembled in various ways due to the arrangement of the various monomers, 20 amino acids and 4 to 5 nucleotides. The number of possible configurations increases with molecule size. Since size and information are correlated, as previously mentioned, most molecules in life are macromolecules responsible for the vast amounts of information that support living systems. Earth consists of about 20 different amino acids. The variable side group R, which consists of various chemicals in each instance, attaches to the fourth bonding site on the central carbon atom. The amino acids that make up the peptide are phenylalanine, R equals CH 2C6H6, serine, R equals CH2OH, glycine, R equals H, and alanine, R equals CH3. The side groups give the polypeptide chain its distinct shape because they are arranged in a particular way within the chain and have varying sizes and chemical characteristics. This configuration produces a distinct three-dimensional structure that, like the components required for a particular chemical reaction, can identify ligands or molecules that bind to it. Deoxyribonucleic acid, DNA, or ribonucleic acid, RNA, comprises long, linear nucleotide sequences. Since both molecules have a lengthy chain of 4 bases, any configuration is possible. N equals 4 to the power of n, where n is the number of nucleotides in the chain, indicates many possible combinations. DNA is a very long molecule with hundreds of thousands of nucleotides that can contain much information. It includes the genetic blueprint for an organism's developmental program and functional capacities. The base pairing rules determine which of the 4 can be paired with any given base. These rules are crucial for nucleic acids because they make information replication easier and enable the base sequence of one strand to act as a template for another. The tenet of modern spacefaring nations' search for extraterrestrial life is to follow the water, since all known life depends on ionic and polymeric chemistry in aqueous solutions. It's unclear if the liquid has to be water. Although water is common throughout the universe and has significant benefits that will be discussed later, we will look at other possibilities. We will begin by stating in general the primary advantages of liquids over solids or gases. The ideal state of matter for enabling the dynamic properties of living systems is a liquid. The following are the essential properties of liquids that make them ideal for biological systems. 1. Liquids maintain their concentration while permitting the flow of different reactants necessary for the complex chemical reactions needed for metabolism. Solid states immobilize reactants disproportionately, whereas gaseous states disperse molecules excessively for normal metabolic interactions. Because the chemistry of life is a team effort, a dynamic yet significant population density of contributors is required. 2. By changing the conformation of macromolecules and biomolecules, liquids promote chemical interactions. For example, protein catalysts or enzymes must have a specific shape to help two reactants adhere to one another or stress a bond that needs to be broken to release energy for other purposes. Water and other polar solvents facilitate the dissolution of polar macromolecules, revealing reactive sites. They also maintain the stability and concealment of nonpolar structures, such as membranes. External chemical influences would be too weak to change molecular configurations in a gaseous state, but they would cause molecular shapes to become unduly rigid in a solid state. 3. Because liquids dissolve substances, individual molecules can easily separate from aggregated forms, move freely, and interact with one another. Reactants stay closely packed and unable to interact with one another in the solid state. The dissociation of salts, molecules bound by ionic bonds, into charged ions is a unique mechanism by which polar solvents dissolve substances. Cellular physiology depends on the concentration and flow of tiny charged ions. A polar solvent is required to dissolve the majority of biomolecules and macromolecules into their constituent units because they are primarily polar. Land-based biological systems are unaffected by nonpolar solvents. However, in other cases, they can significantly impact the behavior of a particular group of reactants, which makes a liquid medium useful for a different kind of chemistry. 4. Chemistry relies heavily on concentration-dependent phenomena, which can be changed by adding or removing reactants from a system. The volume of liquids remains constant. A volume change would affect the concentration of every component, making it more difficult to control the concentration of each reactant and, in turn, its effect. Living things can maintain a stable size by maintaining constant volumes, making adapting to other changing environmental factors easier. 5. The temperature at which liquids exist is between solids and gases. Chemical reactions are greatly impacted by temperature. In a biochemical system, a wide range of temperatures reduces temperature variability. This evidence suggests that we can control metabolic interactions by altering the concentration of particular components. One of the most dependable findings in biology is the metabolic adaptation of biological processes to an ideal temperature, which occurs so frequently. As the temperature of their surroundings changes, organisms adapt to maximize metabolic interactions. Liquids act as thermal buffers, absorbing heat before evaporation and dissipating it before freezing, allowing biochemical systems to operate at lower temperatures than their surroundings. This rule is validated by the exceptions. To survive extreme seasonal temperatures, especially the cold of winter and the heat of summer for some desert amphibians and reptiles, many microorganisms, some plants and some animals, suspend most physiological processes until the ambient temperatures return to a range that allows for effective metabolism and dynamic activity. Seeds and spores stay dormant until the right temperature to resume metabolic activity. In fact, we will show that one possible tactic is to return to a vegetative state resembling spores. Extraterrestrial environments, where ideal living conditions are rare, are where organisms have evolved. After the diatomic gases H2, N2, and O2, water is probably the most common molecule in the universe. Because our planet's average temperature has stayed within the range where water has existed in a liquid state for most of its history, it is particularly beneficial as a medium for complex chemistry on Earth. Water is a polar molecule because oxygen has a higher electronegativity than hydrogen and can draw electrons to its nucleus more successfully. This polarity causes molecules to have low levels of adhesion through hydrogen bonding, in which the partially negative oxygen end of one molecule is drawn to the partially positive hydrogen end of another. Despite having a molecular weight of only 18, this characteristic makes it more difficult for water to separate into separate gas molecules. Because of this characteristic, it can absorb more heat before evaporating than most liquids. As a result, water can retain its liquid state while buffering, absorbing, and releasing large amounts of thermal energy. This procedure provides a wider thermal range for the operation of biochemical systems and stabilizes the environment for biochemical interactions in the liquid. Water's tendency to form droplets on nonpolar surfaces like glass results from the weak cohesion between its molecules, raising surface tension. The concentration in water droplets was essential to the formation of life. However, the small molecule has a low viscosity and can easily pass through other molecules. This characteristic makes it easier for water to pass through channels like blood vessels or membrane pores and allows solutes to diffuse over the necessary distances in a reasonable amount of time. The main advantage of water's polarity is its ability to dissolve charged molecules known as ionizable compounds because of its asymmetrical electron distribution. Na+ and Cl- ions, which operate as separate charged entities, are fully separated in water by salts such as sodium chloride. The movement or presence of these ions is essential to many biological processes. Partial polarization makes macromolecules like proteins and nucleic acids and biomolecules like carbohydrates and amino acids more soluble in water. Most biomolecules comprise nonpolar hydrocarbon chains, such as fatty acids and phospholipids. One end of the chains is made polar by the organic groups that end them, such as phosphates and carboxylic acids. All macromolecules, including water and other polar molecules, may be blocked from passing through the nonpolar areas if they aggregate. However, because of the polar groups on its surface, the entire structure interacts with water easily. The basic chemical makeup establishes cellular boundaries and barriers in an aqueous environment. It is possible to make these structures more complex by introducing tubular proteins across the membrane plane. The tube's upper, lower, and internal surfaces comprise polar amino acids. Conversely, the nonpolar amino acids that make up the tubular protein's outer and central regions mesh well with the nonpolar components of the membrane core. These tubes allow water and other molecules that cannot pass through the nonpolar membrane core to enter and exit the compartment. Finally, water is one of the most important reactants in biochemistry. The first stage of photosynthesis occurs when sunlight causes H+ ions to separate from water. While macromolecules incorporate water to undergo hydrolysis, amino acids, carbohydrates, and nucleic acids remove water to create macromolecules. Water is also an important byproduct of energy metabolism. To maintain its ordered state, maintain its disequilibrium with its environment, reproduce, grow, and in some cases move, life, by definition, requires the consumption and expenditure of energy. Energy harvesting for biological processes may not seem like a big problem, because the universe is full of energy. The question is, how to determine the kind of energy and where it comes from. From our terrestrial vantage point on the third rocky planet from the Sun, 150 million kilometers, 93 million miles, away from the star that gives us warmth and light, we have access to an almost infinite energy source. Light is an extremely effective energy source for organisms that have evolved the capacity to use it. In theory, the smallest unit of light, a photon, has enough energy to affix a terminal phosphate group to 6 molecules of ADP. 6 ATP molecules are produced due to this process and are essential for several metabolic functions. This occurs through a very intricate mechanism. A highly effective photosynthetic mechanism for capturing solar energy and transforming it into carbohydrates and other metabolic intermediates that produce ATP has been developed by plants and some microorganisms over 3 billion years of evolution. What about habitats on other planets like Earth that are too deep for radiation to penetrate, or worlds that are too far from the Sun for its light to be strong enough? How did our planet look before it developed sophisticated photosynthetic systems? What other energy sources, besides sunlight, can power biospheres outside of our own and the inaccessible parts of it? It should be no surprise that chemistry is a major energy source, since life is fundamentally a chemical process. The reactions in the abiotic environment are 5 possible energy sources that living systems could theoretically use. It is noteworthy that they are all oxidation-reduction reactions. When an atom loses electrons, its valence, or tendency to form bonds, increases. Because oxygen is a strong electron acceptor, it can change oxygen's valence by enhancing or decreasing it. When oxygen removes electrons from an atom, like carbon or hydrogen, we refer to the atom that loses the electrons as being oxidized. An additional atom is reduced for every atom that is oxidized. When it reacts with O, it produces H2O, which oxidizes hydrogen and reduces oxygen. The elemental form of sulfur, S, changes from a solid to. The ion of sulfuric acid, HSO4-, is oxidized. Iron, Fe, is the oxidizing agent because its valence is lowered from 3 to 2. When electrons move from shared to more securely held states in molecules, oxidation-reduction reactions release energy as the molecules become more stable. A single atomic nucleus or multiple nuclei may exist. While reducing substances give up electrons, releasing energy, oxidizing agents draw electrons more strongly to their nuclei. Although oxygen oxidizing hydrogen to produce water is highly exothermic, free hydrogen in the environment is unnecessary for this reaction to benefit biology. Some organisms use examples of each of the many other well-known reactions that produce energy yields that are very competitive with sunlight. The complex molecular processes required for photosynthesis indicate that it took a long time to evolve. Oxidation-reduction chemistry most likely acted as the catalyst in the early stages of Earth's existence, converting inanimate objects into living things. Or it might have been the heat. Radioactive decay in planetary cores and atomic fusion in stars both generate heat. As a result, it is widely available and common throughout the universe. In theory, since warmth is a type of molecular motion, chemical reactions easily absorb heat and produce products with higher total energy than their precursors. Thermal sources have the potential to produce much more energy. If all the energy could be used, a water vacuole comprising 10% of a normal microbe could produce 8 million ATP molecules for every cooling degree. The problem is that heat, a highly disordered energy form characterized by molecular motion, causes more disorder when it dissipates. Because most of the available thermal energy contributes to the system's entropy, it can only use a small portion for work. In thermodynamics, the energy required to increase entropy is much greater than the free energy available for work. Thermal energy is ultimately very inefficient. Furthermore, if the heat inflow stops, the heat gradients that promote heat transfer will quickly disappear. If inefficient energy sources are plentiful and consistent, they continue to function. As an example, consider the continuous heat released by a thermal vent. The early stages of a planet's life may be another example in which heat produced during formation provides a constant, powerful internal energy flow. Thermal energy may compete with less powerful but more efficient energy sources when the supply is momentarily limitless. More effective and dependable, albeit weaker, energy forms outperform heat when it is less intense or incapable of maintaining thermal gradients. The current lack of life forms reliant on Earth's thermal energy could be explained by this phenomenon. Heat was a key factor in the beginning of life on Earth, at the beginning of planetary history, before systems for capturing sunlight or managing intense chemical reactions were developed. Every moving object has kinetic energy. Common examples of kinetic energy in various settings include the wind against our faces and the river's current preventing us from swimming upstream. There is, in theory, no reason why living things cannot use this type of energy. Our nervous systems have evolved mechanisms that detect kinetic energy, allowing us to hear sounds, feel the touch of feathers on our skin, and sense the rotation of our heads. Fueled by gravity or convection currents from temperature differences, water movement provides an easily accessible energy source in an aquatic environment, probably the most common habitat for life in the universe. For every 5 square micrometers of impacted surface area, a stream moving at 10 centimeters per second can produce enough kinetic energy to create 1 ATP molecule every second. Compared to sunlight and the majority of oxidation-reduction reactions, this energy yield is lower. However, kinetic energy would be useful without light or suitable reactants. When 2 solutions containing a diffusible material are mixed at different concentrations, the material migrates from the higher to the lower concentration region. Its initial concentration is lowered as the cube compacted sugar diffuses into the larger volume of coffee. Living systems maintain environmental disequilibrium, mainly by containing substances with higher or lower concentrations than their surroundings. As a result, a more concentrated molecule outside of a cell will naturally diffuse inside if allowed. On the other hand, materials inside the cell but not outside will diffuse outward if the cell allows permeability. The concentration gradient between the 2 sides of the membrane, separating one compartment from another, is directly proportional to the diffusion propensity. A living cell can access a potential energy source by being encircled by a solution more concentrated outside the cell than inside. Through channels made to connect the motion of the particles to a chemical reaction that absorbs energy, it can capture the energy of moving particles entering the cell. A cell can convert this kind of energy into beneficial biological processes. The electrical charges of ions create attractions similar to other types of energy, making them useful for diffusing particles. A battery works by separating charges that produce energy when they flow. Ionic gradients can be created by any known biological membrane through various methods. Biological membranes use the diffusion energy produced by concentration gradients to allow certain ions to flow while obstructing others. Hydrogen ions, H+, move along concentration gradients with an enzyme that binds the terminal phosphate to ADP to phosphorylate ATP. Calculations show that a 100-fold concentration difference across a membrane, typical in living organisms, can generate enough energy to create 1 ATP molecule for every 3 ions that flow through the enzyme channel. Despite being weaker than most oxidation-reduction reactions, this reaction is still an essential energy source for organisms in saline environments. Theoretically, organisms in high-salt environments, such as some microorganisms in hypersaline lakes, have access to far more energy than was previously discussed. In fact, it may even be comparable to that obtained from sunlight and oxidation reduction processes. A wilted plant's stiff, healthy structure is restored when water is poured into the surrounding soil. Every woman is aware that salt retention results in tissue swelling and a bloated sensation during the later stages of her menstrual cycle. Osmosis, a particular type of diffusion where water is the diffusing material, is the cause of both phenomena. When a diluted solution is added to compartments with water-permeable membranes, water will migrate from the solution into the contents of the membrane. This phenomenon is due to osmosis, the spontaneous movement of water from a diluted solution into a more concentrated one. Many dissolved metabolites and ions, referred to as solutes, are commonly found in living cells. These are surrounded by membranes that keep them inside while letting water in. Osmosis increases the system's entropy and releases energy by decreasing the difference in solute concentrations on the inside and outside, which makes it thermodynamically advantageous. Within the cell, water molecules flow freely through channels. The energy of a biomolecule like ATP could be increased by using the channel's interconnected molecular machinery to power a chemical reaction. The amount of energy that osmosis can extract depends on how steep the concentration gradient is inside and outside the cell. According to our findings, a difference of 0.7 osmoles, roughly equivalent to 0.6 electron volts between the water surrounding a freshwater fish and its interior, is released for each molecule that enters a fish cell through osmosis. Although this distinction is visually appealing, it allows for the phosphorylation of a single ATP molecule in almost all cases. About 45 molecules of water permeate the system. Because of the higher energy yields from other possible sources, no known mechanism exists for any organism on Earth. However, osmosis might be the life-giving mechanism in a situation where there are no other energy sources. Although magnetic energy is ubiquitous in the universe, previous studies have shown that it is useless in almost all environmental settings, except planets orbiting powerful magnetic sources like magnetars, which are neutron stars with massive magnetic fields. Every star and the planets surrounding it are surrounded by tectonic stress, radioactive decay, ionizing radiation, gravity, and pressure. Could these also be sources of potential life-giving energy? Although we cannot rule out any of these possibilities, energy must be dependable, readily available, and effectively captured by chemical reactions that produce biomolecules to be biologically useful. Although very energetic particles can be released during the decay of radioactive elements, radioisotopes are not evenly distributed, and their energetic emissions are too irregular to be predicted. All stars likely emit ionizing radiation, but their energies are too high for biochemical systems to efficiently absorb. However, magnetic fields are too weak at molecular dimensions to compete with other easily accessible energy sources, even though they are also likely to exist around most stars and many planets. Any solid planetary body may experience tectonic stresses, but only certain minerals can utilize this energy source. Furthermore, it's hard to think of a way to transform it into a form organisms could utilize. Although pressure and gravity are ubiquitous and potent energy sources in the universe, their gradients at the molecular level make them less potent than other equally accessible energy sources. Only the transformation of energy from these exotic sources into forms that are beneficial to biology is discussed here. In some circumstances, their indirect effects might be essential for maintaining life. The heat from radioactive decay in a planet's core rises to the surface by convection, which can be released at thermal vents or hot springs. It can also cause tectonic movements, which in turn cause volcanoes to release sulfur and other oxidizable compounds. On the surfaces of frozen planets and moons, ionizing radiation can liberate oxygen from water ice, which can subsequently initiate chemical reactions that release energy. Primary sources of kinetic energy are too unpredictable, powerful, or disorganized to directly drive biochemical reactions. Examples of kinetic energy include convective currents brought on by differential heating from thermal vents and tidal changes by gravity. Living things benefit from kinetic energy. In conclusion, there is an abundance of energy in the universe. Redox and photonic chemistry enable the minuscule energy exchanges necessary for the structure and operation of living systems. They are not, however, the only possible energy sources. When these are unavailable, we must turn to alternative energy sources. The energy available in that environment must be the first factor to consider when speculating about other planets' evolutionary paths. We begin by defining life, which is a difficult task because our definition needs to be inclusive enough to include all possible forms of life in the universe, and specific enough to exclude natural or artificial phenomena that display traits of living things. The fact that a living thing is both an entity and a process adds to this difficulty. To define a living organism, we suggest three necessary and sufficient criteria. First, it consists of a highly structured system physically separated from its more chaotic environment. Second, it maintains a high level of organization and performs tasks by regulating and converting energy from its surroundings. Third, based on information passed down through countless generations, it self-replicates autonomously, using materials from its surroundings to produce nearly exact copies. Polymeric and ionic chemistry manifest organisms' highly ordered structure and variable properties in biological systems. Large macromolecules called polymers are found in all forms of life on Earth. They consist of chains of carbon atoms joined to nitrogen, phosphorus, or oxygen by a covalent bond. They are both flexible enough to move around and strong enough to remain in one spot. Given the temperatures and the availability of liquid water, which is carbon's natural counterpart, the planet is a perfect place for carbon to serve as the backbone of biological polymers. Despite having chemical similarities and having the potential to serve as a backbone for polymers, silicon would need very different environmental conditions than those on Earth. Biomolecules are carbon-based organic polymers that perform dynamic tasks, build structures, transfer energy, and regulate metabolism, a complicated system of chemical reactions that occurs inside our bodies. The monomeric, or single building blocks for much larger macromolecules, are biomolecules. The three main classes of macromolecules that support life on Earth are proteins, carbohydrates, and nucleic acids. Long sugar chains that store energy are a component of many cellular structures and smaller lipid molecules. Proteins offer shape-specific surfaces for catalyzing and controlling particular chemical reactions, and the building blocks for cellular structures. Any given protein's distinct shape is determined by its amino acid sequence, which comes in roughly 20 varieties. The order in which amino acids will line up in a protein is determined by the long linear sequence of 4 bases that nucleic acids use to encode information. They create the genetic material that is passed down through the generations. We won't know whether proteins, carbohydrates, or nucleic acids, as we know them, exist in other living systems in the universe until we examine samples of extraterrestrial life. However, it is reasonable to assume that wherever life exists, macromolecules of some kind must play analogous roles due to the necessity of storing energy and the high information content of living systems. According to persuasive arguments, biological processes take place in a liquid environment. Liquids facilitate mobility while maintaining critical concentrations. Additionally, they maintain a constant volume, promote chemical interactions by altering molecules' chemical state and conformation, dissolve most substances as separate reactants, and shield living organisms from abrupt changes in the external environment. Water is the perfect solvent for terrestrial life because it dissolves the main macromolecules and makes insoluble lipids, another class of biopolymers. This allows biological membranes to form. A solvent apart from water could serve as a medium for biochemistry that is not seen on Earth under different physical circumstances. To maintain its highly ordered, low-entropy state, aid in self-healing, react to stimuli, develop, and procreate, life depends on an ongoing energy flow from the environment. Energy, light, and oxidation reduction are abundant in the universe, but chemical reactions are especially good at supplying them in a form and quantity that living systems can use. However, even without light or the proper chemistry, biogenesis can be powered by other readily available forms of energy. These consist of kinetic energy, heat, and ionic and osmotic gradients. The possibility of extraterrestrial life depends on certain conditions, mainly the physical environment, which includes available chemical resources and energy sources. Furthermore, life has a past, meaning that its initial circumstances and evolutionary paths substantially impact its final results. After discussing the beginnings of solar systems, the nature of life, the importance of chemistry, and the need for energy, we must consider how life can arise from an inanimate world and grow into the interdependent web of organisms that make up ecosystems. We must approach the topic broadly to ensure that our presumptions apply to the various habitats that may support living things, regardless of their location in the universe. The beginnings of life on Earth remain a mystery to us, and its emergence elsewhere is even less clear. We know much less about the origin of life on Earth than we do about its possible emergence elsewhere and subsequent arrival on Earth through meteorites or other celestial bodies. One potential universal mechanism for spreading life among nearby planets is the interplanetary spread of life, or panspermia. At some point, life had to have begun. An extremely favorable environment for the emergence of life is Earth. Therefore, we will begin with our conclusions about the genesis of life on Earth and generalize from this one example to a larger. We have many theories, but the origins of life are still unknown. We know enough about biology and chemistry to outline a plausible series of phases that early life, at least on Earth, most likely went through. They include the following things: a 9-step model for how life first appeared on Earth. 1. In the primordial waters of the Earth, simple organic compounds like sugars, fatty acids, and amino acids clumped together. Early in Earth's history, they might have been created from simpler molecules like hydrocyanic acid, formaldehyde, ammonia, and carbon dioxide, with energy from meteorite impacts, lightning, and volcanic eruptions. According to radio astronomy and meteorite chemical analysis, they might have come from space. 2. The growing number of organic molecules would have accumulated to a concentration greater than what is currently found in nature if there had been no enzymes or existing life to break them down. If ideal circumstances had existed, such as aridity, high temperatures, or the facilitation of inorganic substrates, condensation reactions might have taken place. Simple organic monomers were combined in these reactions to form larger, more complex nitroglycopeptides. At first, the NGP's composition varied almost randomly, but as synthesis or stability improved, particular chemical configurations became more common. 3 different NGPs might have initiated the formation of larger aggregates or photopolymers during repeated drying and rehydration cycles. These would have differed greatly because of the unique substrate conditions in the area. Some photopolymers might have appeared or remained more common as time passed and awareness of the effects grew worldwide. 4. Fatty acids and other molecular groups are aggregated into spherical or bilayered protomembranes. These molecules have polar heads and hydrophobic tails. Within protocellular structures, these membranes might have held onto ions, organic monomers, and protopolymers. Once selective entry and exit from the protocells were established, the internal solution would diverge from the external solution. An imbalance between the protocell's internal and external solutions would have resulted from these occurrences. 5. It is possible that a complex network of chemical exchanges was started by the close proximity of the reactants and protopolymers. Energy is generally needed to synthesize more complex molecules, while energy is released when larger molecules break down into smaller ones. If combined with an exergonic reaction, reactions with an unfavorable energy input could still occur. Catalysts can accelerate rare reactions, which scientists call reactions with high activation energies. The inorganic substrate or polymers that have gotten large enough to adopt shapes that facilitate substrate binding may contain them. 6. It's possible that some photopolymers concatenated their monomeric units to transmit information. At first, the sequences might have been mostly random, but some might have become more common over time. Their arrangement was originally dictated by an inorganic substrate's shape or chemical properties, like clay. Some sequences have recurred more frequently because of their ability to improve survival. It's possible that these informational polymers eventually developed the ability to replicate themselves, forming the first protogenetic system. 7. The replication mechanisms could have gradually changed to become more accurate and efficient because they were ineffective and imprecise. Occasionally, these informational biopolymers might perform genetic and catalytic tasks. When it became safe to replicate polymers carrying particular information for genetic and catalytic tasks, metabolic regulation most likely started. Scientists believe that the first polymer to acquire these functions in the evolutionary history of life on Earth was ribonucleic acid, RNA. This stage of evolution is known as the RNA world. 8. A division of labor developed as structural, genetic, and catalytic functions improved. Proteins are mainly used as structural elements and catalysts because of their wide range of adoption in three-dimensional structures. Although the structure of nucleic acids is straightforward, a great deal of information can be found in the sequence of their monomers. Because of this characteristic, they are the most effective means of transmitting genes from one individual to another. Translation is the process by which RNA coordinates the proper arrangement of amino acids into proteins and acts as the storehouse of genetic information. Proteins acted as translation templates and catalysts for metabolic processes, enabling RNA replication. 9. Deoxyribonucleic acid, DNA, a more stable nucleic acid, evolved during Earth's evolutionary history to take over the long-term storage of genetic information. This identified RNA as a mediator in the process of protein structure encoding. DNA and RNA are chemically similar and use the same mechanism to store information using a sequence of only 4 different monomers. These properties created a sequential information flow from DNA to RNA to protein. Transcription is the technical term for RNA synthesis on a DNA template. The DNA world, from which all modern life on Earth is derived, was started by DNA being the primary medium of genetic information for all living organisms, with very few exceptions. Of the 9 stages mentioned above, the final 2 are facts. There is still debate, even though most of the first 7 stages have been modeled, and some have been experimentally verified. Many biomolecules common on other planets have been created in the lab from basic building blocks present on the original Earth. This instance is an example of stage 1. The arrival of organic molecules, such as amino acids, on Earth has been well documented by space-based meteorites. Although condensation reactions are difficult to carry out in aqueous environments, they are possible in certain experimental settings that occur naturally. Although it is more difficult to prove empirically, the next level of complexity has been partially achieved. The inorganic substrate may play a particularly important role during this stage. The minerals will help monomers and photopolymers align, encouraging their aggregation into bigger, more intricate molecules. They have this advantage because of their consistent structure and catalytic properties. We have modeled it well, but have not yet reached stage 5, where a certain number of reactants, photopolymers, and polymers interact independently. 8. Replication's origins are still unknown. The preference for particular alignments may be strongly influenced by the inorganic substrate. Experiments aimed at creating autonomous prototypes of proto-metabolism and proto-replication are a thriving field of study that should soon yield significant discoveries. Stage transitions rather than stage characteristics impose the above scheme's limitations. It is particularly difficult to imagine how life on Earth evolved from a primitive form of proto-replication to the sophisticated transcription, translation, and replication processes used today. The development of intricate metabolic and genetic processes occurred in phases that are hard to observe today, like the gradual domestication of animals and the development of symbolic language. The intense disagreement over the order of stages in particular cases qualifies the previously mentioned general theory of life's origin. Whether metabolism can evolve without a previous replication mechanism is the main source of debate. The idea of a self-sustaining metabolic system becomes more plausible when it is realized that adequate metabolism is required to support replication. Currently, proto-metabolism and proto-replication have undergone significant and simultaneous evolution. This will only be supported by extremely reliable models or empirical data. Another point of contention concerns the circumstances surrounding these stages. Protopolymers are believed to form at the interface between the substrate and water. Like tidal pools or ephemeral ponds, they experience drying out and rehydrating cycles. This isn't the only choice. Given that the conditions necessary for life to emerge on other planets are likely to vary greatly throughout the universe, Earth provides several alternative environments, which is beneficial. Scientists have proposed numerous habitats as the most likely places for life to have originated. Prebiotic chemistry may have begun in a warm little pond containing various ammonia and phosphoric salts, which could then be converted into a protein prepared for further complex alterations by light or other energy forms, according to Charles Darwin's 1871 letter to Joseph Hooker. His conjecture could not be elaborated in detail because of his limited knowledge of chemistry at the time. Alexander I, a Russian biochemist, expanded upon these ideas and early experimental results. Oparin suggested that a primeval soup of organic compounds could have formed in the oceans due to lightning or other energy sources in an atmosphere rich in molecules like hydrogen, ammonia, and methane, but lacking oxygen. It happened at the beginning of the 20th century. J.B.S. Haldane, an English chemist, put forth similar ideas in England in the middle of the century. Stanley Miller, a University of Chicago graduate student of renowned cosmochemist Harold Urey, investigated these ideas empirically by exposing a mixture of hydrogen, water, ammonia, and methane to electric discharges. The evolution of organic chemistry in the Earth's primordial oceans was strongly supported by synthesizing different organic compounds, including amino acids. The need for chemists to explain how the earliest amino acids and related compounds formed on Earth from basic precursors has diminished as there is more proof that organic molecules were brought to the planet by meteorites. But organic substances like life must have come from a certain place. Therefore, the question of how biomolecules are synthesized abiotically remains relevant. Using gases considered more representative of the early Earth's atmosphere, we have repeated Miller's experiments many times under different circumstances. As expected, yield and the products vary depending on the original reactants. Organic compounds will inevitably form. The transportation of organic compounds by comets and abiotic synthesis likely produced the building blocks for more complex biomolecules in the early oceans. Because condensation reactions are difficult to induce in a watery environment, it is more difficult to proceed to the next step. These reactions create chemical bonds by removing water, a hydrogen atom from one molecule and a hydroxyl group from another. According to many scientists, certain conditions, like thermal energy, tidal fluctuations, or other factors, must explain how basic building blocks like amino acids can combine to form more intricate structures like proteins and peptides. Sidney W. Fox demonstrated convincingly in the 1950s and 1960s that peptides could form microspheres when amino acids and a mineral substrate were heated to high temperatures. These microspheres might be the first stage of protocell development. While lower temperatures favor some reactions, higher temperatures encourage others. Miller and his colleague Leslie Orgel have shown adenine and guanine, two nucleotide monomers of RNA and DNA, to be best synthesized in ice. 3. Microchannels of liquid brine concentrate organic reactants more as water freezes because the surrounding ice crystals keep dissolved materials out. The procedure lessens the harmful effects of heat while speeding up chemical reactions. Numerous experiments have shown that certain polymers can grow in these circumstances. However, thermal cycling is necessary to produce various modern biomolecules because some nucleotides require high temperatures to synthesize. Another factor to consider is whether the same set was required at the beginning of life. Thanks to the generative potential of the ice-water interface, initial biomolecules may continue to emerge in icy worlds across the universe. The oldest living things in the tree of life, bacteria, flourish in the high temperatures of deep-sea thermal vents and hot springs. The discovery has led to speculation that life on Earth might have originated at the ocean's depths, where temperatures are higher than the boiling point of water, and energy is provided by heat or chemical processes rather than light. The leading proponent of the theory that life first appeared in high-temperature, high-pressure environments through oxidation-reduction processes involving metals like iron, nickel, and sulfur was the German chemist Gunther Wechtershäuser. Wechtershäuser refers to his metabolism-first model as the iron-sulfur world, which would have come before the RNA world put forth by Orgel and others, much like the NGP world that we previously suggested. Since volcanic activity has been detected at several sites throughout our solar system, including beneath several of Saturn's and Neptune's icy moons, this possibility is relevant to our quest for extraterrestrial life. The process of biological change over time is known as organic evolution. The idea that life has evolved is the foundation of modern biology. Evolution is the name given to this process. This book examines the possibility of life evolving on other planets, calling for knowledge of the fundamentals and workings of evolution. We propose that natural selection is the main mechanism of evolution concerning variable characteristics. Contemporary terminology emphasizes the evolution of organism populations. People do not evolve throughout their lives. An animal does not become smaller simply because of a lack of food brought on by climate change-induced long-term decreases in rainfall. However, because smaller individuals naturally have a competitive advantage, the mean size of animals within a population may decrease under such circumstances. Nature selects them to reproduce more frequently than those with larger bodies because they can live on less food. Given the inheritance of body size, smaller survivors will likewise have smaller offspring. A permanent evolutionary change in the characteristic size of animals in a population will result from accumulating the advantages of diminutive size over many generations, lowering the average size of individuals within the population. People who don't understand evolution often portray it as a random process. Randomness does not exist in natural selection. All variants would have an equal chance of surviving if the process were random, and those that did so would only have done so by accident. On the other hand, those with the best chance of surviving are selected by nature, not at random, but because of characteristics that increase their chances of surviving. This does not, however, mean that evolution lacks randomness. Stochastic factors are the main cause of variation within a population of molecules, microbes, or animals. When life began, the initial biomolecules were a rather random collection, whether from abiotic precursors or alien sources. It is assumed that largely random mutations in genetic material account for a sizable amount of the variation seen in populations of living organisms. Although some chromosome segments are more prone to mutation than others, the probability of mutation is still uncertain and essentially random for large chromosome segments. Chance also affects the initial genetic makeup of a new population, especially when a small fraction of a population experiences a disaster or when only a few individuals cross a bottleneck, like a land bridge that spans 2 continents. Take note of the other important steps in the process. It must, therefore, be subject to natural selection. An inheritance mechanism must demonstrate that the trait has a genetic basis. In other words, we will look more closely at each element, section, chance, and heredity, to evaluate the likely paths of various conditions that might occur. Selection works imprecisely before the emergence of a self-sustaining life form. The combinations formed in the early stages of organic compounds joining to form potential biomolecules can be entirely arbitrary and random within the broad range permitted by chemical principles. However, local substrate properties can affect the bonding between some reactants, which may be unique to a particular environment. The same organic molecules can be drawn to the same mineral structure more than once. Reactants that bind to it will adhere more readily in such a configuration. A particular mix of proto-biomolecules will be produced more frequently when bonds are formed, broken, and reconnected repeatedly, possibly at different locations with the same substrates. In the absence of electrically charged sites on substrates, hydrophobic molecules may aggregate preferentially. These water-resistant molecules may eventually clump together to create aggregates or lengthy structures that resemble membranes. These structures can enclose water and trap a variety of biomolecules. Protocells are these things. The molecules of a protocell were largely selected at random and influenced by the characteristics of the substrates. These different reactants may then start interacting in different ways. Compared to other mixtures, some will cause longer self-sustaining reactions. After being disassembled and reassembled using reactants from the prior protocellular generation, certain reactions would either help the protocell survive or increase the likelihood that it would reactivate. Natural selection would operate in a primitive form before forming complex chemical systems. Natural selection will determine the evolution of actual living systems. These systems will eventually develop independent metabolism, cellular structures, and gene transmission mechanisms. Natural selection is not a homogeneous process. Understanding the different forms of selection is essential to predicting likely outcomes in a variety of settings, and thus on different planets. Imagine an animal species widely dispersed throughout a continent's coastal region. Animals at both extremes of the size spectrum adapt slightly less than animals in the middle when they are left alone for extended periods without changing their surroundings. Larger species require more food than is readily available, which accounts for this variation. On the other hand, the smaller species have a harder time staying warm in the winter. The ideal ratio between adequate warmth retention and low food needs is represented by an intermediate size. As the variation range narrows, the population's mean will be determined by natural selection, favoring the survival of individuals closest to the ideal size. This prime example of stabilizing natural selection limits variation around a fixed while resisting change. Assume that a mountain range, similar to the coastal range of California, is gradually raised by geological forces over time. In the colder climate of higher elevations, Individuals of our sample species must now have larger bodies to retain heat. Even if the food supply is adequate to support larger bodies, individuals at the upper end of the size-frequency distribution will be favored over those at the lower end. Individuals that formerly constituted the ideal size of the species are included in this class. People have bigger bodies at higher elevations, which raises the mean value. However, this increase won't necessarily change how much body size variation there is. This instance is a prime example of directional selection, a natural selection that promotes change and the course of environmental changes. The lowland populations now face different conditions depending on where they are in the range. On the leeward side, the recently raised mountain range creates a rain shadow, which increases precipitation on the windward side. The habitats of individuals at similar elevations on either side of the range are different, with coastal populations living in a cooler, more precipitation-rich environment, which increases food availability, and those on the other side experiencing a warmer, drier climate, which decreases food resources. A once single species exposed to a uniform climate has now split into two populations exposed to very different environments. One population favors a larger body size on the coast, while the other favors a smaller one in the desert. Divergent evolution will result with two different mean values coming from the same source. Disruptive selection, a type of natural selection that splits an existing biological group into two descendant groups with different biological traits, is best illustrated by this instance. The two populations will split into different species after achieving reproductive. According to experts, the emergence of new species is preceded by disruptive selection. Determining the viability of life's evolution on other planets will require analyzing these diverse types of natural selection. While some environments are dynamic and constantly changing in their challenges to existing life forms, others have stayed uniform and stable for billions of years. Chance influences the makeup of a star, the features, sizes, and locations of planets in a solar system, and the chemical makeup of each planetary body. Before life began, chance already limited the potentialities of the molecules that make up life, the solvent from which it originates, and the energy source that will drive it. Chance continues to shape the course of life within the confines of the physical world. Theoretically, there are more amino acids known to exist in the universe than in terrestrial life forms. This is partially demonstrated by meteorites, like aminoisobutyric acid, which are not found naturally on Earth. The extent to which natural selection has influenced the reduction of the potential amino acids is still unknown. But there is no doubt that a significant shift in the organic compounds that originated on Earth or were created at the beginning of time influenced the original variety. The original organisms might have discovered it by chance integration into metabolic pathways that support themselves. Wherever life's precursors appear, chance surely plays a role in their formation. Before natural selection favors one or more true cell types and establishes the evolutionary path for life on a planet, which may be largely determined by chance, the first group of protocellular aggregates that attempt to survive is known as the initial assemblage of protocellular aggregates. They're not totally random. It is crucial to understand that randomness may also contribute to the properties of the substrate or other variables. Every molecule, protocell, or organism in a living system varies because of randomness, and this variation serves as the basic substrate for natural selection to promote the emergence of life. Natural selection molds chance-induced variation into life forms best suited to their respective habitats in the opportunistic environment in which living systems are formed. Stabilizing selection tends to decrease variability as soon as natural selection establishes the basic traits of the living system. However, randomness continues to generate variation in living things over long periods through various mechanisms. Above all, the following are crucial. Mutations, which mostly happen as random events, can affect the chemical basis of information storage. It is important for life on Earth that the nucleotide sequence in DNA can be altered by radiation, chemicals, or other physical agents. The genetic message for a gene is altered when a single base in the DNA strand encoding that gene is either destroyed or replaced. The amino acid sequence and consequently the conformation of the gene-encoded protein are altered by this transformation. Sometimes the change is beneficial and may even be preferred by natural selection in the struggle for survival, but it is usually detrimental because natural selection has probably already produced an optimally adapted structure. Most mutations are detrimental, preventing them from continuing. Some mutations are neutral. They alter a DNA segment that does not code for a gene or have such a small effect on protein structure that natural selection is unaffected. As environmental conditions change, some initially neutral mutations may become advantageous or disadvantageous, depending on their value in the new context. The exchange of genetic material is the broadest definition of reproduction. The ability of living things to continuously mix their gene pools, the genes of a population breeding with itself, was greatly enhanced when this process began in the history of life. To create their progeny, each genetically unique organism contributes, male, or receives, female, a distinct sample of the gene pool. This means that the offspring will also be genetically distinct. Natural selection acts again with every generation due to this process, which invariably results in genetic variants that are either advantageous or disadvantageous. Whether variation enhancement is the primary mechanism of natural selection's effectiveness is debated among biologists. However, there is no doubt that natural selection can act on increased variation, leading to a wider variety of gene combinations. A tiny portion of the gene pool sets future generations' course. The founding gene pool may completely differ from the original one. This changes the starting point for the subsequent evolutionary path of that particular group of organisms. The term genetic bottleneck describes this phenomenon. Examples include the establishment of a new population on an island by a small group of mainland immigrants, the movement of a few migrants via a difficult or temporary pathway from one habitat to another, or the survival of a small group of individuals in the event of a natural disaster that wipes out most of the parental gene pool. Compared to the larger original population, populations that experience a bottleneck typically produce descendants with substantially less variation. According to some anthropologists, modern humans are descended from survivors of several genetic bottlenecks between 60,000 and 2 million years ago, when the total number of humans may have decreased to a few thousand or fewer. Researchers consider the Finnish human population, Darwin's finches in the Galapagos Islands, and cheetahs supplemental examples. Humans fit the bottleneck hypothesis because they have little genetic variation. Finch species on each Galapagos island show the founding effect of the original colonizers, but cheetahs and finches are genetically homogeneous. A local segment of any large population may consist of a set of genes that deviate from the population's average composition. Natural selection of new biologically beneficial traits may benefit greatly from this random variation. Additionally, it might condemn the local group to a higher mortality rate. Local variations in genetic composition that occur by chance can be influenced by natural selection. Information about the composition and nutrition of an organism is transmitted through heredity. Earthly life's genetic information is chemically stored, mostly as a series of nitrogen bases along a DNA strand, a large macromolecule that, if linearized, would stretch for miles. Despite its significant folding, it can be encapsulated in the microscopic nucleus of a single cell. Every DNA molecule is copied and passed on to the offspring cell during cellular division. As long as parents continue to have children, genetic information will remain. One of the distinguishing features of living systems is the persistence of the genetic information repository, independent of the organism that transmits it. It is deliberate if this document looks like an essay on information theory. In addition to energy, structure, and function, biology also includes information. Any alien life we find, wherever it may be, will require a system for storing and transmitting information that is part of it, but not dependent on that life form. A simple and elegant solution to this problem is a linear sequence of chemical monomers, like the 4 nitrogenous bases in DNA. Whether a universal method can encode genetic information using a linear arrangement of molecular constituents is one of the most intriguing questions in the search for extraterrestrial life. Will they be similar to those in DNA? Will these components exist in less than 3 different forms? Have you ever wondered what the long-headed, big-headed aliens with the big slit eyes eating in B-grade science fiction movies would be eating? Are any of them portrayed as farmers? Are there any other species that can be kept as pets? Do they participate in photosynthesis if they are green? The eating habits of aliens have rarely been of general interest except in a few experimental episodes of Star Trek or The Twilight Zone. Nonetheless, this is among the most crucial facts needed to assess the scientific viability of any extraterrestrial life form. Organisms evolve in an ecosystem of various life forms that interact intricately. One group's destiny can have a big impact on another. Therefore, interaction with various entities is necessary for all life. At the top of the food chain are sharks and swordfish. Sharks hunt seals, which eat perch, while both eat larger fish like tuna and perch. Smaller fish, like sardines, which feed on tiny invertebrates, are eaten by tuna and perch. Numerous microorganisms and certain plants that inhabit the ocean's upper layers, where photosynthesis is enabled by sufficient light, provide food for smaller invertebrates. On the ocean floor, scavengers like lobsters, clams, and flounders gather decomposing matter from different food chains. Autotrophs, from the Greek word self-feeding, are organisms that get their energy directly from their surroundings, as opposed to indirectly through the consumption of other organisms. Autotrophic organisms are all producers. Heterotrophs are organisms that get their energy from other living or extinct things, other feeding. In the food chain, nutrients move between heterotrophs, where primary consumers eat producers, secondary consumers hunt primary consumers, and tertiary consumers eat primary and secondary consumers. By consuming organic matter from dead organisms, a different type of consumer known as the detrivore helps recycle nutrients. Heterotrophs are common in terrestrial ecosystems and function as primary and higher-order consumers. Primarily, humans eat plants, secondarily, they eat beef, and thirdarily, they eat tuna. Unless it is exclusively autotrophic, any life found on another planet will be a member of a community of organisms that interact extensively. Solar radiation is one of the primary energy sources entering the ecosystem. Simple molecules like CO2 and NH3 are transformed into organic compounds by phytoplankton and other photosynthetic microorganisms producers in the photic zone using light energy. Producers are categorized as autotrophs because they can create their own sustenance from abiotic sources. Another way to group Another name for photosynthetic producers is phototrophs. The producers are eaten by primary consumers like zooplankton. All later consumers rely on the organic compounds that producers synthesize as their structural elements and energy source. Primary consumers are preyed upon by secondary consumers, like small fish. Secondary consumers are preyed upon by tertiary consumers, such as large fish. Heterotrophs, as opposed to autotrophic producers, are consumers. After organisms of any trophic level die, their remains become detritus, which is then consumed by detritivores, some of which may also serve as food. Because energy transfer between levels is inefficient, Energy availability for biosynthesis and maintenance declines as one moves up the food chain. Any given trophic level's total biomass is less than the below levels. The average size of individuals increases at each trophic level as larger organisms, apart from detritivores, tend to consume smaller ones, thereby reducing the total number at that level. Number equals biomass divided by size. At the trophic level, we can graph the total biomass or the total number of individuals. With the highest biomass for producers and the lowest for apex consumers, the graph will look like a pyramid. We can evaluate the makeup of these communities by being aware of a few key facts. Calculating the amount of biomass that power can sustain requires an understanding of the total energy available and its efficiency in converting biomass. Furthermore, if the energy conversion efficiency between successive trophic levels is known, the total biomass for each trophic level can be calculated. If the size of the organisms is known, the biomass can be used to calculate their number. If the number of organisms is known, the biomass can be used to determine their size. This information makes it possible to determine the number and kinds of organisms present at different trophic levels for a given energy input. Numerical data can also be used to describe the community's general structure. For instance, this study aimed to identify possible life on Europa. This information is important for astrobiology and this book because it enables well-informed speculations about the makeup and nature of ecosystems on alien worlds based on reliable environmental data. Unfortunately, the necessary information is often not enough to make any informed guesses about any alien environment. After examining Earth's evolutionary history, we can determine the boundaries of an ecosystem in that environment on that alien planet by restricting fundamental assumptions such as the amount of energy that can sustain the ecosystem. You must comprehend ecosystems and evolution to speculate about how life originated from inanimate matter on other planets. We have proposed several theories about life first appearing on Earth. Since Earth and many other planets in our solar system were flooded with water when they formed, almost all of the suggested schemes take place in watery settings. Most of these schemes have a few commonalities. Some of them presume the existence of organic compounds as precursors, either through abiotic synthesis or delivery from meteorites or comets. Different precursors are periodically brought together by energy-intensive reactions. Normally, these proto-biomolecules would have broken down quickly, but in rare, favorable circumstances, some might have remained into later synthesis cycles, possibly producing a more complex mixture. Highly hydrophobic molecules were probably present in the original aggregates. When not in water, these molecules may adhere to one another in a non-aquatic setting and occasionally form protomembranous barriers to enclose certain organic materials in the water-loving region. Protocells were first introduced. Some protocells had self-sustaining biochemical interactions as they multiplied and became more complex. In some interactions, information that could store and transmit genetic information was replicated self-directedly. The process would be considered living when the metabolic and replicative processes stabilized enough to produce new protocells of the same type from pre-existing ones. Much disagreement exists regarding the scheme's origins, requirements, and details. There is little disagreement among scientists that in the right circumstances, life can develop from non-living precursors. The transition from chaotic and disordered, high-entropy matter to highly structured, low-entropy, self-maintaining entities challenges a mechanistic model. Natural selection is the process that gives the evolution of living things a definite direction. The main process propelling evolution is natural selection, which is impacted by the inherent variation found in biological populations. Natural selection influences the earliest forms of life before distinct species emerge. Random aggregation may occur due to the unpredictable topography of the substrate, and other random factors may make certain component combinations more effective for survival than others. Natural selection sorts these early groups of organic matter, keeping the protocells with the best chance of surviving long enough to make a complete or partial copy of themselves. As natural selection affects the underlying genetic variation, true evolution occurs when a real cell population can reproduce reliably. Genetic variation is produced by sexual reproduction, mutations, and genetic drift. Natural selection is influenced by environmental factors in several ways. Stabilizing selection, which prevents evolutionary change and lessens variation, is favored in stable, homogeneous environments. In environments that fluctuate, directional selection occurs when biological change is induced in a particular direction by selective pressures. Disruptive selection causes new species to emerge due to environmental changes that frequently split a population in different directions. The previously mentioned viewpoint focuses on a single population of organisms, but life develops as a community of organisms linked by intricate food webs that allow energy to circulate among the community. In addition to producing all the organic materials a biotic community needs, autotrophic organisms also capture energy from the abiotic environment to benefit other living things. While secondary and tertiary consumers move these organic nutrients up the food chain, primary consumers absorb them into the food web. In the end, detritivores recycle organic matter from dead organisms' remains. Both consumers and detritivores are heterotrophs because they do not synthesize their food. Each tier of a hierarchical food chain absorbs less energy than the total energy from the tier before it. With fewer organisms and lower biomass at higher trophic levels, this process gives the population and biomass a pyramidal shape. An estimate of the ecosystem structure, including the number and kinds of organisms at each trophic level, can be obtained from the system's energy and several other variables. Even though there is a great deal of uncertainty in the specifics, this knowledge makes speculation about extraterrestrial life a scientific endeavor rather than just an imaginative one. Imagine two intelligent beings, scientists, on a planet circling the star Epsilon Epsilon, which is a little more than 10 light-years away from Earth. They are writing a book on the possible evolution of life in extraterrestrial environments. Their technology is slightly better than ours. For example, they have developed sophisticated remote detection technologies that can gather useful information about solar systems up to 12 light-years away, while we can only detect large planets in these systems indirectly. Like us, they lack high-resolution, close-up photos of these far-off worlds because they haven't yet developed the robotic probes necessary to explore them. They are familiar with our solar system and believe it has amazing potential for life. The Sun is roughly halfway through its life cycle and is thought to be around 5 billion years old based on its size, luminosity, and temperature. According to this data, the 8 planets that can be seen orbiting our Sun are roughly the same age. With their sophisticated telescopes, they can see that 4 of our planets, especially the largest one nearest the Sun, are noticeably larger. They can also see 4 much smaller planets circling the larger ones. According to conventional spectrophotometry, the giants are most likely made up of helium, hydrogen, and nitrogen gases. The small inner orbiting planets have lower volatile gas concentrations, higher densities, and higher silicon contents. As a result, they are categorized as rocky, smaller. Every significant ecosystem on Earth could be split into several communities based only on the climate, Earth's axial tilt, and, to a lesser extent, its eccentricity suggest that its climate changes over time. Temperature increases occur in the northern and southern hemispheres at different times of the year. Winds, precipitation, and global temperature variations would result from differential heating combined with an atmosphere and an active hydrological cycle. The following are the obvious biotic communities that would be affected. Uniform surface heating would produce consistently warm ocean temperatures in the equatorial regions. Even without specific knowledge about habitats like coral reefs, such regions on Earth are expected to be highly productive, maintaining a significant total biomass. As the Moon suggests, diverse life forms may arise from niche fragmentation if the intertidal zone is complex and changes with tidal fluctuations. It is predicted that the temperature of the land masses along the equatorial latitudes will remain warm and comparatively constant. Strong plant growth is implied by such an environment, which also suggests high humidity and significant precipitation. In the tropical zone, plants can grow to considerable height and size due to moderate gravitational force and an atmosphere that is not dense enough to support destructive winds. Under such circumstances, niche fragmentation would be more likely to occur, leading to various forms at every trophic level. The prediction that life in the terrestrial tropics will be more diverse than anywhere else is correct. Organisms acclimated to colder and more variable temperatures would thrive in colder waters north and south of the marine tropics. For someone with a larger frame, this might work. The majority of the primary producers would be phytoplankton and photosynthetic microorganisms. The direction and intensity of ocean currents and precipitation are likely to differ between the tropical and temperate oceanic zones, but it would be difficult to distinguish these subtleties from a great distance. Observers from other planets may surmise that the predominant life forms in tropical and temperate oceans differ. Nobody knows how to describe them. The vast land masses north and south of the equator experience seasonal temperature variations, which are likely to cause variations in rainfall and substantially impact the makeup of biotic communities. The impact is mostly determined by A, the dominant wind patterns, and B, the topography. Large deserts, lush but treeless grasslands, and thick forests are all found in Earth's temperate zones. Different populations of flora, fauna, fungi, and microbes would be found in each habitat. The farther one is from the poles, the more one must adapt to the cold, and the result is a different collection of organisms than in the tropics. Without knowledge of elements like wind currents, precipitation, mountain ranges, continental masses, and other physical features, making accurate predictions about biological details would be impossible. We wouldn't know how life evolved historically to produce the current biota. Streams, rivers, ponds, and freshwater lakes are necessary for an active hydrological cycle throughout the continental land masses. Producers like plants and algae along the waterway's edge would support various freshwater aquatic organisms interacting somewhat with the nearby terrestrial biota. Such a community's animals ought to share evolutionary traits with marine life. There have been geological periods on Earth when the polar climates were relatively cold and temperate. Without a thorough understanding of the polar temperatures, making assumptions about the biotic communities on land or in the oceans near the North and South Poles would not be easy. They probably concluded that biotic diversity is restricted to a small number of relatively large consumers who depend on marine productivity if they were aware of the extreme cold. It's unclear if they would imagine animals like penguins or polar bears, but they could reasonably expect these. The biological characteristics of these organisms must be incredibly varied, considering the possibility of substantial biodiversity on Earth. Examples from a number of the main physiological systems will sufficiently illustrate the point. Numerous complex metabolic pathways are present in even the most basic producers. Chemoautotrophs can extract energy from their abiotic chemical sources and store it in a way that living things can use. Because it is difficult to use photons to create high-energy chemical bonds, phototrophs have even more complex pathways. The development and upkeep of the most basic cells depend on a wide range of biosynthetic pathways and mechanisms for energy release and capture. The focus of metabolism would shift from biosynthesis to consumer-level regulation. Most of the biomolecules that consumers need are produced by producers. Although those nutrients need many modifications, if the basic building blocks, such as specific amino acids or fatty acids, can be acquired straight from the producers, biosynthetic pathways for those building blocks may not be required. The primary function of metabolism shifts from breaking down molecules to regulating metabolic pathways and determining when to activate them as multicellular structures become more complex. Natural selection would shape pathways, considering every organism's unique requirements. Particular metabolic types may emerge to cope with the harsh conditions that some life forms must withstand. Maintaining a constant internal body temperature, or homeothermy, gives animals living in cold climates a significant advantage because it enables them to endure freezing temperatures and stay active while seeking food or shelter. Engaging in such behavior takes a lot of energy, and certain species have evolved especially to produce heat. Water conservation in highly arid environments requires metabolic adaptations. At higher elevations, organisms have to deal with lower oxygen concentrations. These and many other examples demonstrate the wide range of metabolic specializations expected for life on Earth. Assuming that our extraterrestrial authors are not well versed in the reproductive practices of Earth, we base our theories about reproduction on their experiences. At the very least, they would admit that a trustworthy method of copying genetic material and passing it on from parent to child is required. Whether genetic information encoding, as seen on Earth, occurs in life forms with an independent origin, and evolutionary history is a major question in astrobiology. The only conclusive conclusion is that a reliable coding system must be reproducible and generation-preserving. The benefits of sexual reproduction have long been a topic of discussion among biologists worldwide. It is everywhere, from the most basic bacteria to the most complex multicellular organisms. There are many exceptions, though, which suggest that natural selection has weighed the benefits of sexual reproduction against each individual's safer and easier alternative to asexual reproduction. Given Earth's diverse environments and ongoing selective pressures, one might assume that scientists from other planets would recognize that a mechanism for gene change, such as a high rate of mutation, sexual reproduction, or a cellular process like chromosomal crossover, would enable natural selection to continuously obtain new genetic material for use. The ability to adapt is crucial for survival in a diverse and dynamic world, and genetic variability is closely related to adaptability. Plants do not need to move because they have an abundant energy supply. Since their food source is stationary, fungi do not need to move and primarily break down dead organisms. Animals must move to find new producers or hunt down lower-level consumers, acting as prey when the local supply runs out. No matter what names our alien scientists gave to 11 plants, 11 fungi, and 11 animals, they would undoubtedly expect that some would need to move while others wouldn't. Because motility is advantageous, natural selection would pressure some organisms to improve it. If our alien scientists had the intelligence to recognize that the oxidizing atmosphere of Earth supports a high-energy metabolism, they could reasonably conclude that some organisms could achieve high speed. They likely concluded that movement could result in considerable energy expenditure, particularly on land and in an atmosphere with much oxygen. It is reasonable to assume that many motility mechanisms have developed throughout life, such as swimming bladders for buoyancy in fish, lateral body oscillation in fish, flapping wings in birds and butterflies, legs for walking in a variety of animals, limbs for climbing in some species, undulatory movement in worms, and jet propulsion in cephalopods, squid and octopuses. They would be shocked to learn that most animal species on Earth use flight as their primary locomotion. Existence depends on the ability to perceive and respond to biotic and abiotic environments. Even passive organisms like plants turn their leaves toward the light, and shut their stomata to preserve water when the air gets dry. This behavior demonstrates the ability to sense humidity and light. Basic microorganisms have to recognize beneficial chemical compounds and avoid those that could be harmful. Predictably, the chemical senses are the oldest and most common sensory faculties. Taste and smell are the names given by animals to these vital chemical senses. They might be the fundamental component of all living things in the cosmos. Different tactile sensations, such as touch, heat, cold, pain, and pressure. Electromagnetic radiation, which different species perceive as vision or heat depending on the wavelengths that are strongest in their environments. Vibrations in water or air, which more complex organisms interpret as sound. And spatial orientation, which aids living things in maintaining equilibrium in the gravitational field, differentiating between up and down, and determining the direction and speed of their acceleration. Since our alien observers on Earth have identified a wide range of habitats, they probably expect every physical aspect of the environment to be a possible target for detection. They can deduce the cellular specializations for light, heat, and pressure detection based on the traits of life on their planet. The fact that many living things on Earth are believed to be highly mobile indicates that they have a sophisticated system that can process various types of information, combine them, evaluate them using prior knowledge, which indicates that they can recall things, and then respond. Whatever nomenclature is used, we call it a nervous system. Because they rely on passive defensive responses, sedentary organisms can get by with relatively simple sensory systems. Navigating their surroundings forces organisms to deal with a continuously changing range of incoming information and adjust their behavior accordingly. Their information processing systems must advance to become more complex as environmental factors become more numerous or require higher resolution. Organisms need more body mass for coordination as they get bigger. Active organisms require the nervous system or something similar. A nervous system will unavoidably develop in any organ. A large amount of information needs to be gathered, arranged, and coordinated centrally and hierarchically. A brain will develop. A quick look at life on Earth shows that improved cognitive abilities are correlated with advanced sensory processing. More intelligent animals tend to have more developed senses and frequently show multisensorial specialization. Of course, their brains are bigger. On the other hand, not every organism with remarkable sensory abilities is cognitively advanced by nature. Despite their exceptional sensitivity to pheromones, airborne chemicals used to attract potential mates, moths do not appear to have cognitive advantages over other insects. Even though some fish have highly developed brains specialized for electroreception, they are not particularly intelligent. As a result, the relationship between cognitive ability and sensory sophistication is brittle. The most advanced cognitive abilities are found in organisms that can navigate their surroundings, react to changes, and whose behavior depends on the immediate acquisition and processing of large amounts of new information. It makes sense that some big, active creatures that live in various settings, including Earth, would have highly developed cognitive abilities. However, we shouldn't place too much emphasis on cognition. Microbes and plants, incapable of thinking, make up most of Earth's biomass. Although mushrooms, clams, and sponges have little personality, they have long been an essential part of the biosphere on Earth and will probably continue to exist after the more sentient species that share the planet. We contend that for the majority of life on Earth and probably elsewhere in the universe, cognition is rarely the path to evolutionary success. Nevertheless, given the circumstances of our planet, it has appeared in some life forms. Cognition should be equally predictable if those conditions exist elsewhere. There are consequences to cognition. Under the right circumstances, cognition can lead to technological breakthroughs that improve an organism's ability to control and influence its environment. Because of our species' actions, we have this knowledge. If we were positive that someone was watching us from a distance, we would also know it had happened elsewhere. The circumstances described include A. Long evolutionary history with pivotal events like the development of multicellularity and high-energy oxidative metabolism. B. Varied habitats with high levels of habitat fragmentation leading to high levels of biodiversity. C. A plentiful and ubiquitous energy source sufficient to support complex ecosystems with large active apex organisms. D. A changing and dangerous world that requires sophisticated cognitive and social skills. E. Ancestry. In an environment, probably arboreal, that supported the evolution of prehensile hands and improved eye-hand coordination. And F. Terrestrial evolution, where a range of raw materials was easily accessible and fire energy could be used. Were our alien observers aware of these conditions, they would probably conclude that intelligent life forms with the capacity for technological evolution could emerge on Earth. They could detect the radio and other artificial emissions we have been sending into space for a century, and if they could examine Earth closely, they could determine whether it happened. They would have been convinced that there is a technologically advanced life form on Earth if they had kept enough eye on the planet to see the dramatic changes in our atmosphere, including the sharp rise in greenhouse gases and the sudden appearance of mysterious substances like chlorofluorocarbons. They would understand that other intelligent beings are in the universe besides themselves. We created a scenario that accurately depicts our circumstances. We can test the potential usefulness of our speculations about alien life by asking what a distant intelligence with similar technology could infer about us, and then comparing the answers to the reality of life on Earth. According to this movie, significant life insights can be gained by comprehending the planet's age and its basic geochemical and geophysical features. From a distance of 10 light-years, our alien observers could not confirm any details of their prediction, assuming that their technological capabilities are not appreciably better than ours. They may make mistakes. By examining their potential errors, we can better understand how accurate or imprecise our assumptions about extraterrestrial life from Earth's point of view are, given our current knowledge and available technology. A great deal depends on the nature of our observers. They should have no trouble understanding our basic biological traits if carbon-based organisms are soluble in water, but insoluble in humans and participate in biochemistry. They would undervalue our terrestrial biosphere if they were only aquatic and had no sense of life on land. Should their surroundings be oxygen poor, they would undervalue its importance and consider it only a poison or a highly flammable threat incompatible with life on Earth. They would underestimate the frequency of flights as a means of transportation, even though they recognize the possibility of terrestrial life. As a result, they are unaware of how common animals like birds and insects are. Our extraterrestrial visitors would likely have had a difficult time imagining how water-soluble, carbon-based polymeric chemistry could result in the formation of living systems, especially within the narrow temperature range that their theory would require if they had come from a place that wasn't like Earth, such as silicon-based chemistry at much lower temperatures in a non-aqueous environment. They might have hypothesized that kinetoscopes could capture energy from atmospheric movements, oceanic currents, or tidal forces impacted by the Moon's orbit around Earth, since they were aware of the constant variations in Earth's wind and ocean currents. We have not found these organisms because phototrophy and chemoautotrophy are more effective. Calculation error is an example of the faulty inferences that theory can draw without empirical data. Their perception of the possible organisms on Earth may be distorted by size. Their senses would surely focus their attention on looking for creatures on Earth that possessed comparable skills. Their evolutionary past influenced their theories about the extent of evolution on Earth. They would consider the idea of a similarly long developmental stage for life on Earth to be completely conceivable if their evolution as unicellular organisms had taken 2 billion years. They might, however, find it puzzling that a more technologically sophisticated civilization would not exist on a planet that is 4.5 billion years old if its evolution had advanced considerably. Fundamentally, the more closely an alien planet resembles our own, the more similar our evolutionary paths are, and the more likely our observers will be able to correctly identify our nature. Our ability to recognize life forms that resemble us is the only reason we are successful if life in other worlds is comparable to our own. The only, or at the very least, the most preferred form of life in the universe is life essentially the same as us, carbon-based, waterborne. We must use a great deal of intelligence and receptivity to properly imagine the nature of extraterrestrial life if it exists in forms very different from our own. The fact that we haven't found life like ours won't prove it doesn't exist. We must consider these ideas as we consider the circumstances and possible planetary histories of the other worlds we will explore for life. Theoretically, Earth has all the necessary elements for life, such as carbon-based biochemistry, liquid water's widespread use as a solvent, and plenty of sunlight. Along with these advantages, it also has an atmosphere, diverse continental landforms interacting with fresh and saltwater environments, continuous geological activity, and an age of 4.5 billion years, indicating a long history. We have empirical evidence of the emergence, expansion, and evolution of diverse life under these circumstances. A large amount of biomass can be converted at the producer level thanks to abundant water, sunlight, and the possibility of chemoautotrophs. Significant biodiversity results from the extensive habitat fragmentation caused by climates and topography. High-energy oxidative metabolism and cycles of biogenic carbon, hydrogen, and oxygen production and consumption sustain a vast network of food webs spanning numerous trophic levels, encompassing consumers of all sizes, shapes, and activity levels. Evolution has resulted in a slow rise in complexity, but the shifts toward this complexity have been long-term and have always involved relatively few individuals. Life on Earth was exclusively prokaryotic, the most primitive cell type, for the first 1.5 billion years and another billion years before macro-multicellular organisms appeared. The one sample of life we have at our disposal is insufficient to establish whether the long period was a necessary condition or simply a result of the accidental development of life on Earth. It's among the most open-ended theories we can develop about extraterrestrial life. The rate of diversity and innovation increased after life first appeared on land, most likely due to a notable rise in atmospheric oxygen levels. Life has undergone many disruptions and changes, frequently sudden, which are increasingly thought to be caused by catastrophic events like massive meteorite strikes or worldwide volcanic eruptions. Each catastrophe has so far opened up new possibilities. Limited forms of intelligence have been fostered by the convergence of numerous historical and natural conditions. Humans have advanced technologically beyond their biological capabilities due to their distinct evolutionary history, high cognitive ability, and easy access to energy and raw materials for creating tools and machinery. With the help of technology, this species has been able to explore worlds other than its own and search for life forms that are similar to itself, or in previously unthinkable forms. Venus's atmosphere is divided into 4 major zones, 7.1. About 38 kilometers, about 24 miles of carbon dioxide, CO2, are on the surface. A growing haze of sulfuric acid vapor with a decreasing CO2 density is present for the next 10 kilometers. The third zone, which comprises 3 different layers in a CO2 matrix, consists of thick sulfuric acid clouds that rise to a height of slightly more than 70 kilometers. About 45 miles, ca 72 kilometers, sulfuric acid ice crystals, and a diminishing CO2 haze are found in the 4th and highest zone. At the base of the cloud deck on Venus, the air temperature is about 80 degrees Celsius. At about the top of the intermediate cloud layer, it drops to 4 degrees Celsius. Within this same range, atmospheric pressure on Earth fluctuates between 1.1 and 0.3 times that of sea level. Therefore, the two bottom layers of Venus's cloud deck contain temperatures in the liquid range for water at or below pressures similar to those in Earth's atmosphere. The lowest cloud layer covers Earth's normal and thermophilic microbial life between 80 degrees and 33 degrees Celsius. Normophilic to psychrophilic bacteria could easily live in the middle cloud layer at about 3 degrees to 4 degrees Celsius. Thus, organic macromolecules might withstand the temperatures and pressures in Venus's lowest clouds. Even though there isn't much water in Venus's atmosphere, there are a few hundred parts per million in the lowest cloud layer. Water freezes into ice crystals above the middle cloud layer as the temperature quickly increases below the clouds from about 58 kilometers onward. At high altitudes, water molecules are eventually separated by cosmic radiation or UV light. Sulfuric acid is liquid at a single pressure bar across a broad temperature range of 10 degrees to 337 degrees Celsius. As a result, it floats as liquid droplets through the atmosphere from a few kilometers above the surface to roughly the middle layer of clouds, which is around 55 kilometers. The raindrops form a haze about 30 to 48 kilometers above the ground. The sulfuric acid starts to condense into droplets large enough to form opaque clouds at a height of about 48 kilometers. The largest droplets, measuring around 3.6 micrometers in length, are found in the lowest cloud layer because they appear non-spherical. This length corresponds to the size of the water droplets that make up clouds on Earth. Sulfuric acid is extremely hygroscopic, absorbing all available water. Consequently, the droplets are best described as concentrated sulfuric acid solutions with a pH of 0 or lower. The acidity equivalent of battery acid is this value. Acidophilic bacteria are common on Earth at this high acidity level, but chemically harmful to most organic macromolecules. To a significant extent, none of the probes designed to detect organic compounds have succeeded. Organic compounds must be extremely uncommon if they are present in Venus's clouds. The environment lacks organic chemicals from a distance, even though life, particularly microbiological life, is abundant on Earth's surface and atmosphere. There is no lack of vitality in the Venusian clouds. Sunlight, of course, is powerful. Even the lowest cloud levels receive a significant amount of light because enough light passes through to illuminate the surface, even though a large portion is reflected from the uppermost reaches of the cloud deck. Wind speeds range from 50 meters per second, approximately 112 miles per hour, 180 kilometers per hour at the bottom of the lowest cloud layer to 200 meters per second, approximately 450 miles per hour, 724 kilometers per hour at the top of the middle layer, making them strong enough to complete a full circumnavigation of the globe in 3 to 4 days. 3. If any life on Venus had developed the ability to use kinetic energy, it would be abundant. In addition, researchers have discovered lightning in Venus's atmosphere. Lightning could aid in creating organic molecules that could end up in the metabolic pathways that any organism would have to follow, but it would be too powerful and erratic for use by living things. Small amounts of ethane and other organic molecules generated by photolytic or electrical activity in the upper atmosphere were found by Pioneer Venus 2. Furthermore, small molecules can take part in energy-producing chemical reactions. Sulfur oxide, for example, which has been expelled from the interior for billions of years, might react with carbon monoxide and hydrogen to form hydrogen sulfide and a small amount of energy. UV light is absorbed by one component of the Venusian clouds. This ability is possessed by sulfur compounds and photopigments, among other substances. One such molecule is arranged like a ring with 8 sulfur atoms. In a novel reaction similar to photosynthesis, this molecule could be used as an ultraviolet sunscreen. a pigment that absorbs UV light and binds it to high-energy chemical interactions, or a way to change UV light to lower frequencies better for photosynthesis. 4. It is interesting to note that hydrogen sulfide, which is produced when sulfur dioxide is reduced to energy in the first equation above, is concentrated in the atmosphere immediately beneath the lowest cloud layer. This supports the hypothesis that physiological effects could be produced by a chemoautotrophic mechanism in the lower clouds. Whether these reactions are triggered by the metabolism of the biological entities in Venus's clouds is still unknown. According to some scientists, oxidized SO2 and reduced H2S sulfur compounds may exhibit a chemical imbalance that could be utilized to generate energy if the proper molecular machinery can be created. As a result, they turn into biosignatures for life. The sulfuric acid clouds on Venus are much larger and more persistent than the ephemeral nature of clouds on Earth. According to models, the sulfuric acid droplets that make them up span months instead of days as Earth clouds do. A Mode 3 droplet could stay whole and float in Venus's lower cloud layer. This floating drop of aquatic microhabitat may contain a population of microorganisms over several generations of a typical microorganism's life cycle. Mode 3 particles could also be Venusian germs wrapped in sulfur compounds, about the size of earthly bacteria and a few microns across 4. While the concept of flying sulfuric acid islands that are home to a family of bacteria during a 3 or 4 day orbit around Venus is appealing, the realities of such a way of life force us to recognize some challenges. The acidity would be a major obstacle to begin with. As previously stated, the acidic water of hot springs near the boiling point provides the perfect environment for various microbial life on Earth. They undoubtedly require special adaptations, and even then there aren't many known to exist at pH 0. The relative lack of water, however, is another problem. Assuming that any life in the clouds actually resides in liquid droplets of an acid-water mixture is not impossible. They absorb all stray water molecules because they are extremely hygroscopic. Organic reactants are also uncommon. You can create organic compounds by combining different oxidized forms of carbon, CO, CO2, CHOH, nitrogen, and ammonia with UV light or lightning. However, no matter how many probes have been sent to Venus, they have failed to find a clear indication that organic molecules are present at concentrations higher than a trace. There is little chance of a carbon-based biochemistry if Pioneer's finding of 2 parts per million of ethane becomes the norm for organics in Venus's clouds. Any organism eventually finds it difficult to stay buoyant in the air because its density is greater than that of the atmosphere in which it exists. However, the density of sulfuric acid droplets is sufficient to keep everything afloat easily. As a result, the size of an organism is restricted to the area available in its aquatic or aerial home. Notwithstanding the challenges outlined above, potential avenues for the evolution of life in Venus's clouds raise some fascinating questions based on the notion that even a small biomass could survive on the chemical resources in Venus's clouds and offer an intriguing alternative form of extraterrestrial life. Do some forms of life exist in the clouds forever? How could that have happened? How could life created and nurtured on a planet's surface forever reside in its clouds? We argued that Venus may have had a richer and more diverse ecosystem earlier than Earth or Mars. It's possible that life initially flooded Venus's waters. As the planet warmed, fog and low-lying clouds would have been commonplace, and the atmosphere would have grown more humid. Like the sea it came from, the mist would have been acidic. As more carbon dioxide and sulfur dioxide dissolved, the water would have turned sulfuric and carbonic. This would have led to the development of acidophilic bacteria. Acidophiles would have felt very comfortable in the airborne acid droplets as the mist rose from the sea and hung in clouds. The earliest persistent life forms in Venus's clouds would have undoubtedly been acidophilic chemoautotrophs and photoautotrophs. As the microbial populations in the heavens evolved to eat the autotrophs in the waters below, heterotrophs would have gradually joined them. To keep the water temperatures hot, evaporation would initially act as a buffer against the rise in the surrounding air temperature. However, the waters would have gotten warmer as the greenhouse effect accumulated steam. Once more, thermophilic adaptations would have been preferred by directional selection. This implies that the lakes and seas drying up would have been replaced by new species that were better able to withstand heat than their predecessors. Like their homophilic ancestors, the microorganisms would have climbed into the clouds once they were warm enough to be comfortable. On the other hand, the earlier generation of thermophilic bacteria would have risen to higher atmospheric altitudes, where the air would have been warmer than it was below. A more straightforward scenario would be for thermoacidophiles to evolve from their basic acidophilic cloud relatives. When the water evaporated from the surface, two distinct bacterial populations would have existed in the clouds. In colder climates, older normophilic populations would have survived longer. The lower clouds, closer to the greenhouse heat of the constantly thinning atmosphere, would have been inhabited by more recent thermophilic arrivals or descendants. We don't know why there are two layers at the base of the cloud stack, each about 4 kilometers thick, or when Venus's current cloud arrangement was established. The temperature differential between the two layers is within a range that is comfortable to both thermophilic and homophilic organisms on Earth. The quantity and size of sulfuric acid droplets and the interaction of pressure, temperature, and altitude may cause these variations. The temperature range of the lowest cloud layer is 33 degrees to 80 degrees Celsius. The higher one falls between about 30 degrees and the freezing point of sulfuric acid solutions. The two layers of clouds, each representing a distinct heat zone, are separated by a clean airspace. Thermophiles would own the bottom level, while homophiles would occupy the one above. Like populations on different islands, one in the Arctic Ocean and one in the South Pacific, they might have been isolated long enough to be somewhat different above and beyond their different thermal adaptations. In this scenario, before leaving the surface waters of their birth, founding populations of homophiles and thermophiles would have already split due to thermal adaptation, and they would have ascended to the clouds. According to a different interpretation of what happened, the thermophilic adaptation would have happened after the thermophiles in the atmosphere stabilized. Which of these models best describes how the atmosphere gets to its two thermally distinct lower cloud layers? If the atmosphere's temperature remained moderate long after the seas had vanished, then all the life in the clouds would have a thermophilic source. Ecosystem potential in the clouds of Venus. Weight would be a definite disadvantage in an aerial habitat, limiting the evolution of size, even though life in the clouds would severely restrict the growth of consumer size. The small size of the droplets that each microecosystem would occupy would leave little room for larger species, which are frequently found in secondary and higher levels of consumers. The diversity of producers and consumers cannot be accurately estimated. Since the habitats in Venus's clouds are harsh to Earth standards, which is reasonable given that life most likely began on Venus under Earth-like conditions, there is probably little biodiversity. On Earth, diversity is diminished in hostile environments. Only a few types of life on Earth are perfectly suited to the lowest, warm, or next to lowest, colder layer of clouds as producers or consumers. On Earth, autotrophs typically make up the majority of hot springs. In Venus clouds, chemotrophs and phototrophs may recycle abiotic nutrients. This would be consistent with signs of a rather unstable environment. Our solar system's 4 enormous planets, encased in layers of hydrogen and other gases, are typical of gas giants throughout the universe. Therefore, by carefully examining each one, we can rate their life-likeness based on our current understanding. The idea of life existing in Jupiter's or another gas giant's environment is not new. Carl Sagan and Edwin Salpeter suggested in an interesting abstract in 1976 SJ that methane-based photosynthetic organisms would fill Jupiter's clouds instead of CO2 as a carbon source. Organisms that have the shape of thin gas-filled balloons can float steadily. Then they imagined small motorized hunters that could hunt each other down and form sinkers and floaters. The floaters could even have diameters of several meters to kilometers. Flocks of creatures float across the gas giant planets, evading predatory hunts while being pursued by prowling megaflotters of Death Star dimensions. The image is undoubtedly captivating. Can we still assess the viability of these theories over 30 years after they initially emerged in the scientific community? First, let's review what we know about the gas giant planets in general. According to conventional wisdom, our solar system's inner rocky planets and outer gas giants will differ fundamentally. The idea is that the lighter, more abundant elements can congregate around the denser core of rocky material accreted far from the sun without being blasted away by the solar wind. As the planet's mass feeds on itself, more gases, including hydrogen, helium, ammonia, and methane, are drawn to the gravitational well. Eventually, the gas's internal pressure rises. It must be powerful enough to turn it into a liquid, because it will turn into metal when electrons escape their neutrons. The transitions from metal to liquid to gas are barely noticeable above the core. If we came to the planet from the outside with a thermometer and a pressure gauge, we would be met first by clouds of varying heights, depending on their chemical composition and bone-chilling temperatures. As temperatures and pressures rise, they get denser and move deeper into the gaseous environment. We would eventually swim rather than fly because gas turns into liquid under crushing gravity pressures. Sadly, we wouldn't be aware of this because the temperatures would have already reached a point where we could be burned alive. If our chemical kept falling into the Earth's center, it would eventually disintegrate into individual atoms and lose its electrons. Every change would be gradual and at best hazy. Until one arrives at the rocky core of a gas giant, there are no distinct surfaces, liquid, solid, or metallic sea. The temperatures and pressures at that rocky contact with liquid metal are so high that life as we know it is unimaginable. Whether life could exist somewhere in those higher layers, including the clouds at the top of the planet, is still up for speculation. As you can see, the solid centers of all the gas giants are dominated by hydrogen and helium. There are also trace amounts of water, nitrogen, ammonia, ammonium hydrosulfide, and methane. Understanding the relative amounts of these chemical components and the planetary sizes and densities can lead to accurate models of each gas giant's internal structure. These simulations for each of the 4 gas giants in our solar system are contrasted. Everyone's model is different, but there is broad consensus that the 2 smallest, Uranus and Neptune, differ significantly from the 2 largest, Jupiter and Saturn, in that they contain significantly more water, ammonia, and methane. The difference is so great that these molecules form a somewhat thick layer beneath the mantle of Uranus and Neptune, even though not much of it forms on Jupiter and Saturn. Each of the 4 is unique, just like their clouds. Let's quickly examine each one's atmospheric characteristics to assess the likelihood of life among them. 90% of Jupiter's atmosphere is made up of hydrogen, with the remaining 10% consisting of helium and trace amounts of nitrogen, ammonia, methane, sulfur gases, and other organic compounds. Its lower atmosphere was thought to contain water, but the Galileo orbiter and probes found the composition of Jupiter is the most similar to that of the Sun of all the planets. Massive, billowing clouds of different hydrocarbons and their derivatives race beneath the topmost wispy ammonia clouds. Variations in the colorful zone or belt are caused by the different chemicals and condensation temperatures, approximately minus 145 degrees Celsius, minus 229 degrees Fahrenheit at the top of the clouds. The cloud layer descends to a depth 10 times Earth's sea level air pressure, which is room temperature, 21 degrees Celsius, or about 70 degrees Fahrenheit, approximately. 21 degrees Celsius. In these circumstances, water should stay stable as a liquid, but we haven't discovered any water clouds. Jupiter has powerful winds, especially at the equator, where the fastest clouds move at about 110 meters per second, 250 miles per hour, or 402 kilometers per hour. The atmosphere is quite active and turbulent due to the planet's fastest rotation rate, thermal energy released from the interior, heat sinks in the poles, and solar heating at the equator for less than 10 hours daily. About 96% of Saturn's atmosphere comprises hydrogen, with the remaining small amounts comprising helium and trace gases. 3 layers comprise its upper atmosphere: ammonium hydrosulfide at the top, ammonium hydrosulfide at the bottom, and water ice clouds at the top. UV rays are absorbed by the thin ammonia clouds above. The resulting heat obscures the cloud layers below and gives the planet an ambiguous, layered appearance by creating a smoggy haze from the ammonia. It also heats the top layer of ammonia more than the cloud levels directly below, even though temperatures rise again as depth increases. Each of Saturn's poles faces the Sun more directly than its equator for about 7 years due to its roughly 27-degree tilt. The pole oriented toward the Sun has warmer summer temperatures than the equator. During the southern summer of 2004, temperatures near the top of the cloud layer ranged from minus 140 degrees Celsius at the equator to minus 123 degrees Celsius at the South Pole. The temperature at the South Pole was minus 182 degrees Celsius, and the equator was minus 188 degrees Celsius, which is slightly lower in the atmosphere. The bands of visible clouds encircling the planet are caused by this complex thermal profile, the planet's rapid rotation, and the different temperatures at which different compounds in the clouds condense. They are more powerful than those on Jupiter at the equator, moving at 500 meters per second, 1,200 miles per hour. Large shear forces created by zonal and altitudinal variations in wind velocity at some latitudes cause turbulence and powerful storms. The atmosphere of Uranus contains trace amounts of ethane, 2% methane, 15% helium, and roughly 83% hydrogen. The lowest cloud levels are obscured by a blue haze created by Uranus's much higher methane concentration, which absorbs red wavelengths. Clouds with different compositions are visible at other wavelengths. Compared to the serene image that Voyager 2 first observed up close, recent observations indicate a far more active atmosphere. Scientists have observed storm system-like blotches and measured up to 218 meters per second, approximately 490 miles per hour. Voyager 2 recorded a temperature of minus 214 degrees Celsius close to the top of the cloud layers. Neptune's atmosphere is similar to Uranus's, with about 3% methane and trace amounts of other gases, but it contains significantly more helium, 18%, and less hydrogen, 79%. Similarly, because of the high methane content, Uranus and Neptune appear blue to the human eye, and up close, the white clouds are more visible. The higher cloud layers have temperatures ranging from roughly minus 200 degrees Celsius. Neptune has the strongest winds in the solar system at its equator, reaching 600 meters per second, 1,340 miles per hour, which is faster than the speed of sound on Earth. Large-scale atmospheric events on Neptune have been observed and then dissipated over a few days, indicating a somewhat dynamic environment, according to Voyager 2 and subsequent research. The nearly Earth-like rocky core of Neptune may be covered by an ocean of liquid water in its interior atmosphere. This massive ocean of liquid water rises to the atmosphere of hydrogen, helium, and methane, along with silicates, methane, and ammonia. Given the extreme pressure, the ocean must remain liquid even though it must be burning and in a supercritical state. 8. Life in the midst of the gas giant planets is difficult to speculate about due to the disappointing lack of precise knowledge about their atmospheres. We know enough to appreciate that each is extremely dynamic, even violent by Earth-based standards, with intricate structures, chemistries, and temperatures that vary with latitude, depth, and seasons. At the distance of the gas giants, especially as far away as Uranus and Neptune, solar radiation is still powerful enough to affect weather patterns, but it is much less intense. At higher pressures and lower elevations, heat is a plentiful source of energy. Above all, the kinetic energy of winds is always present in the higher atmospheres of all gas giant planets, and it is far greater than that of the strongest cyclones on Earth. We can confidently state that the temperature of liquid water falls within a range of 0.1 to 10 bars. On Neptune, liquid water might exist at much deeper depths, with much higher temperatures and pressures. The existence of biomolecule precursors within, above, and below this zone may also be contested. Theoretically, organic or even biochemical substances could locally aggregate into microorganisms, although their concentration is typically very low. On Jupiter and Saturn, clouds are dense, while on Neptune, they are dense locally. Though their temperatures are cold enough to support cloud condensation, clouds also probably float beneath the methane haze near Uranus's summit. Lower areas, where air density and temperature increase to accommodate liquid water, have little water. There is no area on any of the gas giants that resembles Venus's bottom layer of clouds with mode 3 particles. It is possible to assess the viability of life in the environment of the gas giants from an environmental perspective. Opportunities are presented by the abundance of energy and chemical precursors for biomolecules. Additionally, there are ecosystems in places where temperatures and pressures do not conflict with the stability of macromolecules, despite their lack of boundaries and poor definition. Historical context is what's missing. When we talk about historical context, we mean a clear picture of the origins of whatever life might have existed there. The strong possibility of life in Venus's clouds stems from the planet's vast biosphere on the surface, which is home to species that have adapted over time to survive in the harsh environment of airborne life. Planets accumulating under conditions that produce a continuum from extreme cold in a vacuum to high heat under great pressure cannot be thought of as such a primordial ecosystem. Even if life could have begun for a short time, it is unlikely that any life could have survived the spike in temperature and pressure caused by the formation of a gas giant that is incompatible with macromolecular stability. In particular, Jupiter and Saturn appear unlikely to be the launching pads of life due to their lack of organic precursors alone. They aren't completely absent, of course. The atmospheres of both planets are rich in sulfur complexes, nitrogen molecules, and trace hydrocarbons. It's unclear if these molecules will ever accumulate to a level where they can take part in complex chemistry. Since methane and ammonia are the primary ingredients, the case for Uranus and Neptune might be easier. The presence of oxygen may lead to the development of amino acids in the right conditions. However, oxygen is limited on the gas giants. Even without it, amino acids wouldn't be considered living. There are no limits or interfaces where self-organizational complexity could gain traction in today's gas giants. Furthermore, the areas where temperatures and pressures might, in theory, maintain macromolecular stability were torn apart by winds, radiation, and upheavals that occur so frequently that it is hard to imagine establishing and upholding boundary conditions, which is what our definition of living systems requires. Given these stringent regulations and the fact that non-living events, like methane, can just as well explain the majority of biomarkers, we can argue that it is unlikely that life exists anywhere in the atmospheres of our gas giant planets. We might be surprised by foreign gas giants, We already know enough about exoplanets to know that some of them are gas giants very different from our own. They will by no means be limiting cases, even though ours is typical of the majority of gas giants in the universe. It is known that planets orbit other stars, in contrast to the gas giants in our solar system. Scientists have discovered planets with masses greater than Jupiter, orbiting less than an astronomical unit, the distance between Earth and the Sun, from their central star. There are probably double and triple gas giants out there that revolve around each other at close range. In addition to the numerous planetary systems that have formed around double and triple stars, what are their historical origins? If, as we contend in great detail in this book, history is fate for life in the universe, we can hardly rule out the possibility of life on planets whose past we do not yet understand. Could life have started because of the formation of a planet the size of Jupiter close to a central star? Until we can definitively rule out the possibility of life existing in the environment of gas giant planets, it is still a possibility. One is inspired by the chemistry and vitality that dance around the top of a gas giant like Jupiter. A time-lapse film of Jupiter's stratosphere in motion suggests that the entire planet is a brooding, roiling furnace of something that seems to be alive. Inspired imagery of a great red spot churning about the planet for at least 3 centuries, perhaps even producing small offshoots of herself in something akin to fission, if not true reproduction, makes it easy to get carried away. But in the end, these are merely phony copies of certain elements of life, undoubtedly created by incredibly active but wholly abiotic processes. Could the massive, swirling whirlpool of activity contain a complex network of organic chemistry, including important precursor product interactions that produce and degrade molecules that are beyond the scope of traditional atmospheric science? Perhaps, even if not constrained by the limits of the thin-walled balloon-like floaters that Sagan and Salpeter envisioned, something akin to floating clouds of complex chemistry, churned into life by the great forces of wind, temperature, and pressure unthinkable on Earth, organisms a kilometer across, could hold their contents through hurricane-force winds that lasted for years. However, we are urged to remove such occurrences from our pantheon of life in the universe by our definition of life in Chapter 2. Furthermore, there is no precise procedure for replication. The test for living entities has yielded negative results, and the absence of a clear physical boundary automatically disqualifies the most lavishly dynamic activity pool from being considered alive. But that doesn't mean that strange things can't happen in the gas giant planet's higher atmospheres, where there is a lot of energy and complicated chemistry. These phenomena are hard to describe in terms of basic physical processes if they aren't fully alive in a formal sense. Life in the clouds is possible because Venus most definitely lived below the clouds. We deny that life could exist in gas giant atmospheres because we don't know how it got there. Let's say this assumption is incorrect. The possibility that life from a common ancestor may have been dispersed on rocky planets through interplanetary transport, panspermia, has been previously investigated. The problem of life's non-origin on the gas giants would have been resolved if panspermia had taken place. If some life had been able to hitchhike from a distant point of origin to the vicinity of a gas giant planet on a wandering asteroid, settling into its rich atmosphere and seeding it with life forever, the question of origins would have been settled. Generally, this is an unlikely scenario for 2 reasons. First, since the outer planets are so far from being the only planet believed to support life, it seems unlikely that a hitchhiking progenitor would survive even on Mars. Second, any type of life that survives would have a hard time adapting to the environment, which is very different from its origin. There is one problem with this way of thinking, though. From the gas giant's clouds, panspermia may have come from a distant source where conditions may have remained unchanged. If life were to exist on Io, which is only 0.003 astronomical units away from Jupiter, It would do so in a radiation environment with recognizable chemistry at extreme temperatures, not that different from any combination of conditions in Jupiter's atmosphere. If there is life on Titan, a scant 0.008 of an astronomical unit from Saturn would come from a satellite that is well equipped with a dense, cold, and biological environment that is hardly different from areas of Saturn's atmosphere with similar conditions. This could be achieved with a relatively limited form of panspermia. However, what is the likelihood that life has developed on these distant, smaller satellites at the edge of our solar system? Before moving on to that subject, let's take a quick look at life in exoplanet clouds. Small, rocky planets like Venus have secondary atmospheres, while gas giants have primary atmospheres. Exoplanets in the middle orbit too close to their star to have a primary hydrogen and helium atmosphere, but are large and warm enough to form a dense secondary atmosphere. These exoplanets may differ from the extremes of our gas giants and Venus's clouds. As an example, let's look at the planetary system Gliese 581. At least 4 planets are currently thought to be orbiting a small M star or red dwarf that is 20.7 light-years away from Earth. The innermost planet, 581e, which has a mass of 1.9 Earth masses, appears to be too close to the red dwarf to maintain an atmosphere, let alone liquid water. The second innermost planet, 581b, is the largest of the 4 with a mass of more than 15 Earth masses. Even so, at only 0.04 astronomical units, much closer than Mercury is to our Sun, it would be a runaway greenhouse planet like Venus if it were large enough to support an atmosphere. Gliese 581c is smaller and farther away, with an Earth mass of 5 to 10. At 0.07 astronomical units from Gliese 581, it might be just far enough away and massive enough to retain an atmosphere and liquid water if the atmospheric pressure and cloud, albedo, brightness, are adequate. The fourth planet, Gliese 551d, is between 7 and 14 Earth masses and is located 0.22 astronomical units from its central star. On the surface of rocky continental masses or even beneath the frozen surfaces of enormous oceans, it might be sufficiently heavy and hardly warm enough to maintain a dense, humid atmosphere and possibly some liquid water. There is a good chance that some species may live for extended periods of time, possibly permanently, in the airborne habitat of their clouds if life is found in the oceans or rocky surfaces of these 2 outer planets in the Gliese 581 system. An energy source, possibly light or radiant heat from the nearby red dwarf. Circumstances that permit the stability of physical boundaries, and a means of reproduction would be typical survival requirements. We would assume that life began on the surface and moved to the atmosphere, as is the case on Earth and Venus. As a result, life in rocky exoplanet clouds would be substantially the same as life on Earth. The communities of living things may be more diverse and advanced than on Earth, and possibly even Venus, and the living things may be more numerous in denser but not much more dynamic atmospheres with an abundance of chemical resources and electromagnetic energy. In those conditions, airborne populations on those distant worlds could attain the complexity of benthic ocean or arid land habitats. All of the planets in our solar system, with the exception of Mercury and many of the larger moons, have atmospheres that range from extremely dense to thin and tenuous. Theoretically, there is no reason why some ecosystems couldn't support life, provided that energy is available and the right chemicals are present. This chapter first examines the hypothesis that life that is most likely impossible to support beneath the clouds of the gas giants and Venus, the densest atmospheres in our solar system, could exist there. The possibility that exoplanets that are in between gas giant planets and rocky planets with clouds could also harbor airborne life forms is then briefly discussed. The atmosphere of Venus is at least 80 kilometers, 50 miles, thick. Lower pressures and temperatures are too high for the stability of macromolecules. However, the planet is constantly moving and is covered in a 20-kilometer thick layer of clouds, the majority of which are sulfuric acid droplets. Two distinct layers float at the bottom of this world's cloud cover, each about 4 kilometers high. The bottommost layer is made up of 3 different sized droplets, the largest of which is similar to the aerosol droplets that characterize clouds on Earth. The temperature ranges from about 80 degrees to 33 degrees Celsius, 176 degrees to 91 degrees Fahrenheit, and the atmospheric pressure is nearly equal to sea level on Earth. The next layer is cooler, with pressures similar to those found on Earth's mountain summits, at about 30 degrees to 4 degrees Celsius, 86 degrees to 37 degrees Fahrenheit. Microbial life finds a comfortable home on Earth under these conditions. Living among Venus's clouds is a challenging experience. Obstacles include a somewhat dry habitat, in addition to the water absorbed inside the sulfuric acid droplets, their high acidity, the lack of organic molecules in significant concentrations, and their enduring hurricane-force winds. However, directional selection might have pre-adapted bacteria to withstand heat, acidity, and aridity if life flourished in Venus's surface waters prior to them boiling away, and they would eventually need to survive in the sky. According to a plausible theory, thermophilic bacteria gradually settled in the cooler clouds that make up the higher of the 2 bottom layers, while thermophiles occupied the lower, warmer layer. It is not impossible for simple ecosystems, including phototrophic and chemotrophic producers, to coexist in the larger droplets in the 2 lower cloud layers. They probably rely on chemical cycles that are partially maintained by both producers. It is much less likely that life could begin and spread in the gas giants' atmospheres. The winds are significantly stronger, the radiation environments are intense, and there is little to no water present. However, the top atmospheres of Jupiter, Saturn, Uranus, and Neptune might contain a slightly higher proportion of organic molecules and do not have the extreme acidity of clouds on Venus. Theoretically, a biosphere could be contained in the tiny areas of each planet's atmosphere where temperatures and pressures are compatible with macromolecular stability. The primary problem with life on the gas giants is figuring out how it could begin without the distinct limits and sensible temperature and pressure combinations that we think are essential for the genesis of life. Given our limited knowledge of gas giants, it would be premature to declare life impossible in their atmospheres in general, especially those that we now know exist in solar systems very different from our own. Unless we can invoke a plausible scenario for seeding by panspermia, perhaps life arising on one of their nearby satellites, for the 4 gas giants in our solar system, we rate the possibility that life could exist anywhere within them as very low. Somewhere in the depths or heights of their enormous atmospheres, chaotic pools of chemical interactions swirl around, alluringly complex but falling short of being alive. Exoplanets with features halfway between those of the main atmospheres of gas giants and cloud-covered rocky planets like Venus are now known to exist. They present yet another opportunity for flying life to exist. They would only alter the theme of life as it occurs on Earth, in its seas, on and beneath its surface, and in its atmosphere, should living things also be found beneath their clouds. On December 15, 1970, the Soviet lander Venera 7 sent both good and bad news back to Earth via radio. On the surface of another planet, it was the first man-made object to do so. Fortunately, it had fallen on Venus gently enough to stay intact and continue to speak. It would not last long at 470 degrees Celsius and 90 times the air pressure of Earth, according to the alarming news. 23 minutes after touchdown, it did indeed die. Venera 7's demise wasn't wholly unexpected. 8 years ago, the spacecraft Mariner 2 passed within 35,000 kilometers of Venus, making it the first spacecraft from Earth to do so. Mariner 2 searched for a dense, continuous cloud cover that stretched 73 kilometers into the sky, suggesting a dense, heavy atmosphere after spotting a heated surface. When Venera 4 successfully parachuted into the atmosphere in 1967, but malfunctioned 25 kilometers above its landing spot, it confirmed Venus's gloomy nature. Despite its beauty in our night sky, Venus is unquestionably the most deadly planet in our solar system. Venus and Earth are nearly identical in terms of size and elemental makeup. The worlds of Earth and her twin are quite different. Since its day, one rotation on its axis, is longer than its year, one orbit around the Sun, Venus, the second of the 4 rocky planets away from the Sun, nearly but not quite achieved gravitational synchronization with the Sun. Even though Venus receives 117 Earth days of sunlight, its surface temperatures are nearly identical at 460 degrees Celsius, 860 degrees Fahrenheit, during the day and night. This is due to the atmosphere's high heat conductance, which is several times denser than Earth's, and the strong winds that blow toward the poles, which quickly and evenly disperse the heat throughout the planet. There is little weather to talk about, just a suffocating, oppressive hothouse at an unrelenting, crushing pressure. Because the strong winds near the top of the atmosphere don't produce any wind at the surface, and the lack of water that has long since boiled away means there isn't any rain. Our morning or evening view from Earth shows a star that resembles a jewel. The extreme heat trapped beneath the clouds is the result of an unchecked greenhouse effect. This happens as the Sun's sacred light, which travels through the clouds but cannot escape, is absorbed by the thick sulfuric acid clouds and carbon dioxide-heavy atmosphere, along with heat from the planet's core. We have a clear picture of what the surface of Venus would look like if we could see through the clouds. Thanks in large part to the extensive surface radar mapping of the Magellan mission in the early 1990s and the fleet of spacecraft sent to the planet by the US and the former USSR. By using cold colors for low elevations and warm colors for high elevations, Venus's topography is color-coded to center at 0 degrees